Picture yourself standing at the base of the Great Pyramid of Giza, feeling the immense weight of 45 centuries pressing down upon you. You're not just another tourist snapping photos. You're a detective standing at the edge of humanity's greatest unsolved mystery, staring at a mathematical puzzle carved in stone that continues to baffle the brightest minds of our modern age. This isn't just ancient architecture, it's a coded message from our ancestors, waiting for us to decipher its secrets, all around our planet, from the windswept plains of Stonehenge to the jungle-shrouded temples of Angkor. These monumental structures whisper stories of mathematical genius that we're only beginning to understand. Why would civilizations from thousands of years ago embed such sophisticated mathematical concepts into their most sacred structures? What drove them to encode the golden ratio into Greek temples, align their buildings with celestial movements with pinpoint accuracy, and work with mathematical constants like pi centuries before these concepts were formally defined? These aren't just random coincidences or happy accidents, they're deliberate choices made by architects and builders who possessed knowledge that we're still struggling to comprehend. They built these monuments to last millennia, ensuring that their mathematical secrets would survive for generations to come, waiting for us to finally unlock their meaning. Today, we're embarking on an extraordinary journey across time and space to explore 30 of these unsolved mathematical mysteries hidden in ancient monuments. We'll decode the numbers that connect humanity's greatest architectural achievements to the cosmos itself, questioning everything we thought we knew about our ancestors' understanding of the universe. This is more than just a history lesson, it's a revelation that will change how you see these iconic sites forever. Get ready to discover the mathematical genius etched into stone and prepare to see our shared human story in a completely new light. To truly appreciate the mathematical wonders we're about to explore, we need to step back and understand the unique mindset of these ancient builders. This wasn't just about stacking stones or carving pillars. It was a profound fusion of function and faith, where every measurement held a deeper meaning. Long before the invention of calculators or even the widespread use of written numbers, these master architects possessed a startlingly sophisticated grasp of mathematical principles. They saw the world through a lens where the practical need for a stable structure was completely intertwined with a spiritual desire to connect with the cosmos. For them, building a temple wasn't just an engineering project. It was a way to materialize divine order on Earth, to create a permanent anchor between the human realm and the heavens above. Consider the ancient Egyptians who used intricate unit fractions to divide grain and land with impeccable fairness, then applied that same precise logic to orient their pyramids with the cardinal directions. Or the Maya, whose complex calendar systems, built on a base 20 numerical system and the revolutionary concept of zero, allowed them to track planetary cycles across vast stretches of time with breathtaking accuracy. These mathematical concepts were far from dry, abstract academic exercises. They were the essential tools used to raise monuments that would stand for millennia, structures designed to align with solstice sunrises, specific stars, and the very rhythms of the universe itself. These buildings were the physical embodiment of a culture's deepest values and their understanding of cosmic harmony. Esteemed scholars like Otto Neugebauer, who dedicated his life to studying ancient astronomy, and Giorgio de Santillana, who explored the transmission of mythological knowledge, have put forth a compelling argument. They suggest that many of these magnificent structures served a dual purpose. They were both temples for worship and incredibly sophisticated observatories for mapping the sky. The knowledge of mathematics required to achieve this wasn't scribbled in textbooks to be forgotten. It was encoded into the very dimensions, alignments, and geometries of these stone giants. This was knowledge meant to endure, to be passed down through generations not by fragile parchment, but through the immutable language of architecture. This deep, inseparable integration of precise math with powerful mythology forces us to ask some truly profound questions. How did cultures separated by vast oceans and continents seemingly arrive at similar mathematical conclusions? Was it a case of independent discovery, a natural evolution of the human mind grappling with the same practical and spiritual problems? Or do these recurring patterns hint at something even more extraordinary, the faint echo of a lost global civilization, or a shared source of knowledge that has since vanished from history? As we journey through these 30 mysteries, remember that each ratio, each alignment, each number is more than just a data point. It is a story of breathtaking human ingenuity, of a relentless drive to measure, to understand, and to find our place in the vast, mysterious universe. Now let's turn our attention to one of the most celebrated examples of this mathematical harmony, a structure that has captivated mathematicians and artists for centuries. High atop the Acropolis in Athens, the Parthenon stands as a testament to the ancient Greek pursuit of perfection. When you first see it, you're immediately struck by its balance and grace, an almost supernatural sense of rightness in its proportions. This is not an accident. Many scholars argue that the source of this beauty is the deliberate application of the golden ratio, a specific mathematical relationship known as phi, approximately 1.618. This irrational number, which cannot be expressed as a simple fraction, appears throughout the Parthenon's design. If you take the overall width of the temple's facade and divide it by its height, the result comes remarkably close to phi. The same relationship emerges when you examine the spacing between the massive Doric columns or the dimensions of the inner sanctuary. It's as if the entire structure is a symphony composed with this one recurring mathematical theme. To understand why the Greeks might have been so drawn to this number, we have to look at the world around us. The golden ratio isn't just an abstract mathematical concept. It's a pattern that nature herself seems to favor. You can find it in the elegant spiral of a nautilus shell, where each chamber grows in size by a factor of phi. It's present in the arrangement of seeds in a sunflower head and the branching of veins in a leaf, all following this same efficient and beautiful pattern. The Greeks, particularly philosophers like Pythagoras, believed that such mathematical harmony was the underlying language of the universe, a divine blueprint. By embedding this ratio into their most sacred temple, dedicated to the goddess Athena, they were essentially building a bridge between the earthly and the divine, creating a space that resonated with the very order of the cosmos. Of course, this leads to a fascinating and ongoing debate among historians. Was the use of the golden ratio a conscious, intentional design choice by the architect Phidias and his team? Or is it a beautiful coincidence that we, with our modern knowledge, are projecting onto the past? We know the Greeks were deeply studying geometry and proportion. Euclid described the golden ratio, though he didn't call it that, in his Elements around 300 BC, which was after the Parthenon was built. This suggests the knowledge was circulating in intellectual circles. Furthermore, Phidias himself was renowned for his sculptural precision and understanding of ideal form. It seems entirely plausible that he and the architects Ictinus and Callicrates would employ the most aesthetically revered ratio of their time to create a building that felt perfectly harmonious. They didn't have our modern decimal point for 1.618. but they could construct it geometrically using a compass and straightedge, dividing a line into what they called extreme and mean ratio. Yet some skepticism is healthy. The Parthenon has been damaged over the millennia by wars, explosions, and erosion. Taking precise measurements today of the original intended dimensions involves some interpretation and reconstruction. Critics point out that if you measure enough aspects of any complex structure, you're bound to find some ratios that approximate phi purely by chance. However, the prevalence of this specific number in so many key elements of the design makes a strong case for its intentional use. It's more than just one measurement. It's a pattern that repeats, a design philosophy made manifest in marble. Whether by meticulous calculation or an intuitive eye for beauty that naturally landed on this proportion, the result is the same. The Parthenon remains a powerful example of how mathematics and art are not separate disciplines, but two different expressions of the same fundamental truth. It challenges us to consider that the tools for creating timeless beauty are not just found in physical materials, but in the invisible, eternal language of numbers. But if the Parthenon's use of the golden ratio feels sophisticated, prepare to have your entire understanding of ancient knowledge completely redefined by the mathematical secrets locked within the Great Pyramid of Giza. This isn't just a tomb for a pharaoh. It's a monument that continues to reveal layers of numerical genius that defy easy explanation. Consider this one staggering fact. If you take the pyramid's original base perimeter and divide it by twice its original height, the result you get is 3.14159, a value that is remarkably, almost unnervingly, close to the mathematical constant we know as pi. This is the ratio of a circle's circumference to its diameter, a fundamental cornerstone of geometry that wouldn't be formally calculated and defined by Western mathematicians for another 2,000 years. The sheer improbability of this alignment emerging by chance in the largest and most precisely built stone structure of the ancient world forces us to confront a monumental question. Did the ancient Egyptian architects somehow possess an advanced, perhaps even ritualistic, understanding of this irrational number? The implications of this possibility are profound. We know the Egyptians were brilliant practical mathematicians, as evidenced by the Rhine papyrus and other texts that show their methods for calculating areas and volumes. But encoding pi into the very dimensions of Khufu's pyramid suggests a conceptual leap from mere arithmetic to a more abstract, symbolic mathematics. One compelling theory proposes that this was not a direct calculation of pi, but rather a clever and intentional representation of circular geometry within a square structure. The Egyptians were deeply preoccupied with cycles, the cyclical flooding of the Nile, the daily journey of the sun god Ra across the sky, and their core religious belief in death and rebirth. The circle was a powerful symbol of eternity and perfection in their cosmology. By designing a pyramid whose height related to its perimeter in the same way a circle's radius relates to its circumference, they may have been creating a massive stone metaphor. The pyramid, a square base representing the physical earth, could have been designed to symbolically contain the essence of a circle, representing the eternal and the divine. It was a way to fuse the earthly and the celestial, the mortal and the eternal, in one perfect architectural equation. This line of thinking leads to an even more expansive and controversial idea. Some researchers, looking at the pyramid's scale and proportions, suggest its dimensions might also encode information about the Earth itself. The pyramid's original perimeter, for instance, is remarkably close to 1/2 of a minute of latitude at the equator, scaled down by a factor of 43,200. While these correlations are hotly debated and often dismissed as numerologic Chinese letter by mainstream Egyptology, their persistence invites speculation. Could there have been a lost, advanced understanding of our planet's dimensions? Or were these alignments, if intentional, purely symbolic, a way to create a model of the world, a microcosm for the pharaoh's journey to the afterlife? Ultimately, whether this pi correlation was a product of deliberate design, a happy coincidence of a chosen slope angle, or a cultural intuition expressed through geometry, it stands as one of history's most captivating puzzles. It challenges the linear narrative of scientific progress and forces us to humbly reconsider the depths of knowledge achieved by ancient civilizations. The Great Pyramid doesn't just tower over the Giza plateau, it casts a long shadow over our modern arrogance, reminding us that the language of mathematics is ancient, universal, and still holds secrets we are only beginning to decipher. While the pyramids and the Parthenon represent the mathematical ambitions of advanced, centralized civilizations, our next mystery takes us to the windswept Salisbury Plain in England, to a monument built by a culture with no written language, Stonehenge. This iconic circle of standing stones, erected over 4,000 years ago, presents a puzzle of a different kind. It's not necessarily about a specific constant like pi or phi, but rather the tantalizing possibility of a lost, standardized system of measurement, a prehistoric tape measure that was used across vast stretches of ancient Europe. This is the mystery of the megalithic yard, a concept proposed by a determined and meticulous Scottish engineer named Alexander Thom. In the mid-20th century, Thom embarked on a monumental task, personally surveying over 600 Neolithic stone circles and other megalithic sites across Britain and France. He wasn't just an armchair theorist, he was out in the field with a theodolite, taking incredibly precise measurements of the placements, diameters, and spacings of these ancient stones. As he compiled his vast dataset, a startling pattern began to emerge. The dimensions of these sites weren't random, they seemed to be based on a common unit of length. Thom concluded that the builders had used a standardized measurement he called the megalithic yard, which he calculated to be approximately 2.72 feet, or about 0.83 meters. What makes this so significant is the consistency of this unit across hundreds of sites and a period spanning centuries. It suggests that disparate Neolithic communities, separated by great distances, might have all been using the same ruler, so to speak. This immediately raises a profound question. How could such a standard be maintained across time and geography without a central authority or a system of written notation? Thom himself proposed several fascinating theories for the yard's origin. One of the most compelling is that it was derived from astronomical observations. He suggested that by measuring the swing of a simple pendulum, perhaps a stone on a string, and counting its swings over a specific period of time, like the number of swings in one day, a builder could reproduce a consistent length. Alternatively, the length could have been calibrated by observing the movement of stars across the sky, using the human body as a crude sextant. This points to a society that was not just monumentally ambitious, but also deeply attuned to the rhythms of the heavens, using the clockwork of the cosmos to define the very units they used to build their earthly temples. Naturally, such a radical idea has its skeptics. Some archaeologists argue that the evidence for a universal megalithic yard is overstated, that Thom's statistical analysis might be finding patterns in what is essentially random noise or regional variations in measurement. They point out that building with massive stones would naturally lead to some rough standardization based on the human body, like a pace or a fathom, which could appear similar across sites without implying a formal, shared system. Despite these criticisms, the sheer volume of Thom's data and the recurring presence of this specific measurement unit remain difficult to entirely dismiss. If his hypothesis is even partially correct, the implications are staggering. It suggests a prehistoric network of knowledge exchange where ideas, units of measure, and engineering principles were shared across cultural groups. It implies a level of sophisticated planning and precise execution for Stonehenge and other sites that moves them out of the realm of primitive ritual and into the sphere of complex, coordinated engineering projects. The story of the megalithic yard ultimately does more than just propose an ancient unit of measurement. It fundamentally changes how we view our Neolithic ancestors. It reminds us that the drive for order, precision, and mathematical consistency is not a modern invention. Even in the so-called Stone Age, humans were seeking to impose a measurable harmony on their world, to create lasting monuments that resonated with a sense of deliberate, calculated purpose. They may have lacked writing and metal tools, but they possessed a sophisticated understanding of geometry, astronomy, and standardization that allowed them to collaborate on a grand scale, leaving behind stone riddles that we are still trying to solve. Just when we might be tempted to view mathematical history as a straight line from ancient Greece to the modern world, a small, unassuming clay tablet shatters that entire narrative. Discovered in what is now Iraq, the Plimpton 322 tablet dates back to around 1800 BC, over 1,000 years before the Greek mathematician Pythagoras was even born. And what is inscribed on this Babylonian artifact is nothing short of revolutionary, a meticulously organized table of numbers that we now call Pythagorean triples. These are sets of 3 whole numbers that perfectly satisfy the equation a squared plus b squared equals c squared, the very same relationship that defines the sides of a right-angled triangle. The presence of this tablet is a stunning revelation. It means that the so-called Pythagorean theorem was not just understood, but was being actively used and applied by Mesopotamian scribes for practical purposes centuries before it was formalized in Greece. So what were these ancient mathematicians doing with this knowledge? This wasn't abstract academic exercise. The Fertile Crescent between the Tigris and Euphrates rivers was a cradle of civilization, and with civilization came complex problems of administration and construction. Imagine the annual flooding of the rivers, which was a blessing for agriculture but a nightmare for land surveyors. Each flood would wipe away the boundary markers between fields, leading to disputes over who owned what. The Babylonians needed a reliable, mathematical way to re-establish perfect right angles on the land to divide it up fairly. By using ropes knotted in the lengths of these Pythagorean triples, say 3, 4, and 5 units, they could stretch them out to form a perfect right angle every single time. This practical application of advanced geometry was essential for maintaining social order and economic stability. It was mathematics in service of society, a tool as vital as the plow or the irrigation ditch. But the application almost certainly didn't stop at farmland. This sophisticated understanding of angles and triangles would have been absolutely critical for the Babylonians' most ambitious architectural projects, their massive tiered temple towers known as ziggurats. These structures were not just buildings, they were stairways to heaven, literal bridges between the world of humans and the realm of the gods. Their construction required immense precision. A slight error in the angle of a ramp or the alignment of a tier could lead to catastrophic collapse. The knowledge encapsulated in tablets like Plimpton 322 provided the mathematical foundation to ensure these colossal structures were not only stable but also perfectly oriented. Some scholars suggest that the precise angles derived from these triples may have held deeper symbolic significance, aligning the ziggurat with specific celestial bodies or cosmological principles, making the structure itself a conduit of divine order. This discovery does more than just add an earlier chapter to the history of mathematics. It fundamentally rewrites the book. For a long time, the story of math was told as a predominantly European journey from the Greeks to the Romans and into the Enlightenment. The Plimpton tablet forcefully challenges that Eurocentric view. It places a profound mathematical insight squarely in the heart of the Middle East, reminding us that innovation is a global tapestry, woven from threads of practical need and intellectual curiosity from all corners of the ancient world. The Babylonians didn't need a Greek philosopher to give them a theorem. They discovered it for themselves through the messy, demanding work of building and maintaining a civilization. Their legacy is a powerful testament to the idea that mathematics is a universal language, one that emerges naturally from the human need to solve problems, measure our world, and reach for the heavens. While the Babylonians were using mathematics to measure the earth and the Greeks to create ideal forms on the other side of the world, the Maya were using numbers for a different, even more ambitious purpose: to master time itself. Their achievement stands as one of the most sophisticated intellectual accomplishments of the ancient world, a complex calendar system of such staggering accuracy that it continues to inspire awe and disbelief. Carved into the steps of the Temple of Inscriptions at Palenque and the walls of countless other monuments, these weren't mere decorations. They were permanent records of a cosmic clock, a mathematical model of the universe designed to track the movements of celestial bodies across vast, almost unimaginable stretches of time. The most famous of these is the long count calendar, a linear count of days from a mythical starting point that allowed them to calculate dates millions of years in the past or future. But the true genius of the Maya wasn't just in counting days. It was in the breathtaking precision with which they synchronized those days with the actual rhythms of the heavens. Consider the solar year, the time it takes for the Earth to orbit the Sun. Our modern Gregorian calendar calculates this as 365.2422 days. Somehow, without satellites, telescopes, or even optical lenses, the Maya arrived at a value of 365.2420 days, a difference of just 17 seconds per year. This level of accuracy is simply astonishing. They achieved it through generations of meticulous, naked-eye observation, carefully noting the precise position of the sun on the horizon at sunrise and sunset, tracking its slow journey north and south over the seasons. This wasn't just an academic exercise, it was the very foundation of their society. Knowing exactly when the rains would come was a matter of survival, dictating the planting and harvesting of their crops. The calendar was their agricultural almanac, a guide for survival encoded in stone. Their astronomical prowess extended far beyond the sun. They tracked the synodic period of Venus, the 584 days it takes for the planet to return to the same position in the sky relative to the sun, with equal precision. They understood its cycles of appearing as the morning star and the evening star, and they invested these cycles with great religious significance, often timing wars and the ascension of rulers to its movements. They also carefully monitored the cycles of the Moon and Mars, weaving all of these celestial dances into a single, intricate chronological tapestry. To manage this incredible feat of cosmic accounting, they needed a mathematical system powerful enough to handle enormous numbers and complex calculations. This is where their other revolutionary innovation comes into play: a base 20 or vigesimal numeral system, and one of the earliest known, fully developed uses of the concept of zero. Unlike our base 10 system, which grew from counting on 10 fingers, the Maya system likely incorporated toes as well, giving them 20 digits as a foundation. This allowed for very efficient notation. They used a simple but elegant system of dots for units up to 4, a bar for 5, and a shell symbol to represent 0 as a placeholder. This concept of zero is a monumental intellectual leap. It's not just an empty space, it's a number in its own right, a crucial tool for performing place value notation and complex arithmetic operations. With this tool, Mayan priest astronomers could add, subtract, multiply, and calculate with a facility that was unmatched in most of the ancient world. They could compute cycles lasting hundreds of thousands of days, reconciling the slightly mismatched periods of the Sun, Venus, and other bodies to create a grand, unified calendar that could predict eclipses and planetary alignments far into the future. The fact that they chose to inscribe these vast calculations so prominently on their most enduring temples speaks volumes about their worldview. For the Maya, time was not a linear progression but a sacred, cyclical force laden with meaning. Specific dates were associated with specific gods and energies. By understanding and predicting time cycles, they believed they could commune with the divine, appease the gods, and ensure the continued order of the cosmos. The calendar was more than a tool, it was a covenant between humanity and the universe. The enduring mystery is how they achieved such precision. How many generations of anonymous watchers spent their lives carefully recording the skies? What complex rituals of correction did they employ to keep their calendar in sync over centuries? Their methods are lost to us, leaving only the silent, stone testimony of their results, a mathematical monument to human curiosity that challenges our assumptions about what ancient civilizations were truly capable of understanding. Leaving behind the precise calendars of the Maya, we now journey to the heart of India, where architecture takes on a different, more organic form of mathematical expression. Here, we aren't looking for a single constant like pi or a standardized unit of measure, but rather a pattern of growth, a sequence that seems to pulse through the natural world. As you approach a magnificent temple like the Kandariya Mahadeva in Khajuraho, your eye is immediately drawn upward, following a breathtaking cascade of stone spires, or shikaras, that seem to blossom from the structure's core like a stone mountain range reaching for the heavens. This isn't a random, chaotic pile of rock. There's a profound, rhythmic order to its complexity. Many scholars and architects have observed that the proportions governing this visual symphony bear a striking resemblance to the Fibonacci sequence, a pattern where each number is simply the sum of the two that came before it, 1, 1, 2, 3, 5, 8, 13, and so on into infinity. This particular sequence is famous for its intimate connection to the way life expresses itself. You can find it in the unfurling petals of a rose, the spiral arrangement of seeds in a pine cone, and the elegant curve of a nautilus shell. It represents a pattern of efficient, beautiful growth. When this pattern is translated into architecture, as it appears to be in the recursive layout of the temple's mandapas, or halls, and its soaring shikaras, it does something remarkable. It creates a building that doesn't feel static or man-made, but one that feels alive, as if it grew naturally from the earth itself. The spaces between pillars, the height ratios of successive spires, the plan of the entire complex, they often correspond to these Fibonacci ratios, creating a visual harmony that is instinctively pleasing to the human eye. For the devout Hindu, this wasn't merely an aesthetic choice, it was deeply theological. The temple is designed as a symbolic representation of the entire cosmos and a conduit for spiritual energy. By using proportions that mirror the very patterns of creation, the architects were building a bridge between the microcosm of the human worshipper and the macrocosm of the divine universe. The act of moving through these mathematically ordered spaces, from the outer halls toward the innermost sanctum, was meant to be a journey of spiritual ascent, aligning the individual's soul with the harmonic order of reality itself. A crucial and fascinating question arises, one that echoes our discussion of the Parthenon. Was this intentional? did the master architects, the Esthapotties, knowingly use the Fibonacci sequence? The honest answer is that we lack any explicit Sanskrit texts that lay out the Fibonacci numbers as a design principle. The mathematical texts of the time were incredibly advanced, dealing with profound concepts of infinity and zero, but a formal description of this specific sequence as we know it isn't found. This leads many historians to caution against projecting our modern mathematical frameworks onto the past. However, to stop there would be to miss a far more profound point. The builders operated within a vast and sophisticated tradition of Vastu Shastra, the ancient science of architecture and design. This tradition was deeply informed by meticulous observation of nature, or Prakriti. They spent their lives studying the proportions of sacred plants, the forms of animals, and the geometry of the human body. They understood that certain proportions simply felt right, that they created a sense of balance, harmony, and life. So, while they may not have called it the Fibonacci sequence, they were undoubtedly channeling its principles. They were replicating the mathematical patterns they revered in the natural world, guided by an intuitive or culturally ingrained sense of sacred geometry. This represents a different kind of genius, not the explicit calculation of a constant, but the embodied understanding of a universal pattern of growth and form. This beautiful ambiguity makes the temples of India not less mathematically significant, but perhaps more so. It shows us that mathematics can be woven into the very fabric of a culture's spiritual and artistic expression without needing to be formally notated in a textbook. The Fibonacci-like rhythms of Khajuraho are not a hidden code waiting to be cracked, but a visible, palpable expression of a worldview that saw no separation between the mathematical, the natural, and the divine. The temple itself becomes a living equation, a prayer in stone that uses the language of natural growth to facilitate a worshipper's growth toward enlightenment. It stands as a powerful testament to the idea that some of humanity's deepest mathematical intuitions are expressed not through cold calculation, but through the warm, living breath of art and devotion. Now we venture into a far more abstract and elusive mathematical territory, one that seems, at first glance, to be a complete anachronism. Our next concept is Euler's number, represented by the letter E, and approximately equal to 2.71828. This is the base of the natural logarithm, a fundamental constant that governs rates of growth and decay, from compound interest to the spiral of a galaxy. Its formal definition and widespread use are firmly products of the 17th and 18th centuries, the work of European mathematicians like Jacob Bernoulli and Leonhard Euler, from whom it takes its name. To even suggest its presence in the ancient world feels like a historical stretch, and yet, when we turn our attention to the sophisticated mathematical traditions of ancient India, we find a series of intellectual sparks that suggest a conceptual understanding, a groping toward the idea, centuries before it was named in the West. This isn't about finding the number E carved into a temple wall. It's about uncovering the profound theoretical groundwork that made such a discovery possible. The evidence lies not in stone, but in palm leaf manuscripts, particularly in the breathtaking work of the Kerala School of Mathematics and Astronomy. In the 15th century, a mathematician named Jayastadeva composed the Yuktibh Amacron letter 1, E63 Amacron, a monumental text that, among other things, laid out detailed explanations for the infinite series expansions of trigonometric functions like sine and cosine. To grasp the significance of this, imagine trying to calculate the precise value of a sine wave not with a calculator, but by adding and subtracting an endless, elegant pattern of fractions. This is exactly what these scholars achieved. They discovered series that converged to these values, and in doing so, they were playing with the very same mathematical fire that would later illuminate calculus and the properties of E. While they didn't isolate the constant itself, their mastery of infinite series and limits demonstrates a conceptual framework sophisticated enough to eventually contain it. They were building the intellectual toolkit, the very language needed to describe exponential growth and continuous change. This raises a fascinating and subtle question. If this advanced theoretical math was being discussed by scholars, did it ever leave the page and influence the physical world of architecture? Could the shadow of E be found in the curve of an ancient stupa or the arch of a temple gateway? The connection is indirect but compellingly plausible. Consider the great stupas like the famous one at Sanchai. Their domes are not perfect hemispheres. They often follow a subtly elliptical or parabolic profile, a curve that requires a sophisticated understanding of geometry to construct. While there's no inscription crediting the use of a specific infinite series, the master architects, or aesthepotes, were undoubtedly educated in the prevailing mathematical ideas of their time. Their knowledge wasn't segregated into pure and applied categories. The same intellectual culture that produced the YUKTIBH Amacron letter 1, E63 Amacron also produced these monumental structures. It is entirely reasonable to propose that the mathematical intuition for handling continuous curves, developed through these theoretical advances, informed the practical calculations and geometric constructions needed to bring these elegant forms to life in stone and brick. The stupa's perfect curve, then, becomes a silent testament to a theoretical genius that was centuries ahead of its time. This story fundamentally challenges the traditional, Eurocentric timeline of mathematical discovery. It moves us away from a simple narrative of isolated genius and linear progression from the Greeks to the Enlightenment, and toward a far richer, more complex tapestry of global innovation. The journey of E wasn't a single lightbulb moment in a Swiss study. It was a slow dawning across continents and centuries. The Kerala mathematicians may not have pinned down the constant, but they built the conceptual runway from which it could eventually take flight. This suggests that major mathematical breakthroughs are rarely sudden inventions, but are more often the final, formal recognition of ideas that have been simmering in the intellectual subconscious of humanity for a very long time. The history of mathematics is not a relay race with a single baton, but a chorus of voices, sometimes separated by oceans and millennia, all humming different parts of the same universal tune. The case of Euler's number in India reminds us that our understanding of the past is always evolving, and that the seeds of our most modern ideas are often hidden in the forgotten footnotes of ancient genius. Moving from the abstract theoretical landscapes of India, we find ourselves stepping into the stark, sun-baked sands of ancient Egypt, where numbers took on a power that was both deeply spiritual and intensely practical. Here, mathematics was not merely a tool for calculation. It was a sacred language, a means of communicating with the gods and securing a place in the afterlife. Within this rich numerological tradition, prime numbers held a particularly potent and mystical significance. Unlike composite numbers, which can be divided into smaller, equal parts, primes stand alone, indivisible by any number other than one and themselves. To the Egyptian mind, this mathematical indivisibility made them perfect symbols of uniqueness, strength, and eternal protection. They were seen as incorruptible, whole, and complete ideal attributes to be woven into the very fabric of their most sacred architecture. This symbolic use is powerfully evident in the sprawling temple of Karnak, a vast complex dedicated to the god Amun-Ra. As you walk through its towering pylons and immense hypostyle halls, the number 7 makes its presence known in subtle but deliberate ways. 7 was a number of profound perfection in their cosmology, associated with the 7 heavenly bodies visible to the naked eye and the 7 stages of the soul's journey. But its power was also rooted in its primal nature. Archaeologists and Egyptologists have noted that certain processional ways were lined with 7 statues. Specific altars were designed around groupings of 7, and crucial architectural ratios within the inner sanctuaries often resolved to this prime number. This was far more than a decorative whim. By embedding the prime number 7 into the temple's design, the priests and architects were invoking its indivisible protective energy. They were creating a sacred space that was mathematically fortified, a divine fortress whose dimensions themselves served as a permanent spell against chaos and decay, ensuring the temple would stand as an eternal conduit to the gods. The application of this principle extended beyond temples and into the realm of the dead, where the need for protection was even more urgent. The dimensions of royal tombs and sarcophagi often incorporated prime numbers in their length, width, or volume. While a modern engineer might choose dimensions for easy divisibility and material efficiency, the Egyptian master builder often seemed to prioritize numerological significance. A burial chamber whose volume was calculated using prime numbers was, in a sense, cryptographically sealed by mathematics itself. It was a space that could not be divided or broken down, mirroring the eternal, indivisible nature of the soul they sought to protect. The prime number became a metaphysical lock, a guardian encoded in stone, ensuring the deceased's safe and uninterrupted journey to the afterlife. This practice reveals a worldview where every measurement was a conscious choice laden with meaning, where the architect was as much a priest and a magician as he was an engineer. Of course, we must approach this idea with a degree of scholarly caution. Unlike a clearly inscribed Pythagorean triple on a Babylonian tablet, the evidence for the intentional use of primes in Egyptian architecture is often circumstantial and interpretive. We cannot find an ancient papyrus that explicitly states, "Use the prime number 7 here for protection." The proof lies in the persistent patterns that emerge when we measure these structures and cross-reference them with what we know of Egyptian religious beliefs from other texts and iconography. The recurrence of certain primes in contextually significant places is simply too consistent to be dismissed as mere coincidence. It points to a sophisticated cultural code, a hidden layer of meaning in their sacred geometry that we are still learning to read. This challenges us to expand our definition of what mathematics was to ancient cultures. For the Egyptians, it was a holistic discipline that encompassed art, religion, science, and magic. The prime numbers in the walls of Karnak are not just mathematical curiosities. They are the silent, stone prayers of a civilization that truly believed the universe could be understood and even influenced through the divine and eternal language of numbers. From the mystical primes of Egypt, we now travel to the sun-drenched world of ancient Greece, where philosophy and form merge to create an entirely different kind of architectural magic. Here, the quest was not for protective numerology, but for the very essence of perfection itself. The Greeks believed that the chaos of the visible world was merely a flawed reflection of a higher, perfect reality, a realm of ideal forms. And for the philosopher Plato, the most perfect of these forms were the 5 Platonic solids. These are the only 3-dimensional shapes that can be built where every single face is an identical regular polygon. Every angle is equal, and every edge is the same length. They are the tetrahedron with its 4 triangular faces, the stable cube with 6 squares, the octahedron of 8 triangles, the complex icosahedron with 20 triangles, and perhaps the most mysterious of all, the 12-sided dodecahedron. Plato didn't just see these as interesting geometric toys. In his dialogue Timaeus, he assigned each one a cosmic element, proposing that these 5 perfect shapes were literally the building blocks of the entire universe. The tetrahedron was the element of fire, sharp and penetrating. The cube was steady, solid earth. The octahedron was air, and the icosahedron was fluid, flowing water. The dodecahedron, however, was reserved for something far grander. Plato rather cryptically suggested that the god used it for arranging the constellations on the whole heaven, making it the shape of the cosmos itself, the container for all of creation. This wasn't just abstract philosophy discussed in dusty academies. It was a worldview that profoundly influenced the very stones of Greek civilization. If these five solids were the divine blueprint for reality, then what greater purpose could there be for an architect than to incorporate these perfect forms into the temples dedicated to the gods? The idea was to create a microcosm, a small, perfect model of the universe here on Earth. While we won't find a massive stone dodecahedron serving as a temple's roof, we might find their essence encoded in the design. For instance, the spatial organization of a sanctuary might be divided into 12 sections, mirroring the 12 pentagonal faces of the dodecahedron, perhaps aligning with altars for the 12 Olympian gods. The cubic form is readily apparent in the simple, stable base of many structures, representing the solid earth upon which the temple stands. The octahedron and icosahedron, with their numerous triangular faces, might find expression in the complex triangular pediments that crown the facades or in the geometric patterns of intricate mosaic floors. The goal was to use this sacred geometry to create a building that wasn't just beautiful, but that was fundamentally true, resonating with the same mathematical harmony that governed the stars. We must tread carefully here, as this is one of the more speculative connections. Unlike finding a specific number in a pyramid's ratio, we are looking for the ghost of an idea, a philosophical influence on architectural proportion. There are no surviving architectural plans from ancient Greece that explicitly say, "Now place the column to align with the vertex of an imaginary icosahedron." The evidence is more circumstantial, rooted in the overwhelming importance of geometry in Greek thought and the clear desire to create ideal proportions. Architects like Ictinus, who designed the Parthenon, were undoubtedly educated men, steeped in the philosophical currents of their time. They would have known of Plato's theories and shared the cultural desire to make the ideal real. When they chose the proportions for a temple's cella or the spacing of its columns, they were likely thinking in terms of geometric purity and harmonic ratios. The Platonic solids represent the ultimate expression of that purity. So while a Greek temple may not be a literal, oversized model of a dodecahedron, its design philosophy is deeply dodecahedral. It strives to capture the essence of cosmic order and perfection. It is architecture as philosophical statement, a physical prayer built from the conviction that the universe is, at its heart, profoundly and beautifully mathematical. Now, let's journey across the Atlantic to a world where mathematics took a form so revolutionary it would fundamentally reshape human thought. Yet it was recorded not on parchment, but in bark paper, books, and carved into stone stelae in the humid jungles of Mesoamerica. We are talking about one of the most profound intellectual inventions in history, the concept of zero. For a long time, the history of mathematics was told with a distinctly Euro-Asian flavor, crediting Indian mathematicians like Brahmagupta in the 7th century with its formalization. But this narrative completely overlooks a parallel, and in some ways even earlier, genesis of zero in the Americas. The Maya, along with other Mesoamerican cultures, independently invented and used a true zero, a full placeholder and number in its own right, centuries before it made its way to Europe. This wasn't a fleeting idea. It was the very engine of their sophisticated calendar systems and astronomical predictions, meticulously recorded in surviving texts like the Dresden Codex. To understand the sheer brilliance of the Mayan zero, we first need to grasp their unique numerical system. Unlike our base 10 system, which grew from counting 10 fingers, the Maya used a base 20 or vigesimal system. This likely incorporated a count of all 20 digits, fingers and toes as a natural foundation. Their notation was elegant and efficient. A dot represented 1, a horizontal bar represented 5, and to represent the absence of a value, they used a powerful and unmistakable symbol, a shell. This shell glyph, or seichin in some contexts, didn't just mean nothing in a passive sense. It was an active placeholder that allowed for the unambiguous expression of numbers like 20, which was written as 1 dot in the second position above a 0 shell, or 400, which was 1 dot in the third position above 2 zeros. This system allowed them to write any number, no matter how colossal, with perfect clarity. It was this powerful tool that enabled the Maya to perform the complex, long-term calculations required for their obsession, time. The most spectacular application of zero is found in their calendar, particularly the long count. This was a linear count of days from a mythical creation date, allowing them to pinpoint any day in a vast continuum of time. Imagine trying to write the date 2024 without a zero. It would be impossible in a place value system. The Mayan long count date works the same way. A typical date might read something like 9 backtons, 14 catons, 3 tons, 0 winnels, 12 kins. That zero in the winnels place is absolutely critical. It tells the reader explicitly that in the progression of time units, the winnel position is empty, ensuring the date is read with perfect accuracy. This precision was vital for their astronomy. They calculated the synodic period of Venus to an astonishing 584 days, tracked solar years with remarkable accuracy, and predicted eclipses. None of this would have been computationally possible without the operational power of zero. It was the linchpin that held their entire cosmic model together. This leads us to a fascinating and more subtle question. If zero was so central to their calculations of time and space, did it also influence their physical world, specifically their architecture? While we don't have explicit construction manuals stating, "Place this stone at coordinate 0, the concept was almost certainly implicit in their planning. The Maya were master urban planners, designing cities like Tikal and Palenque with precise alignments to celestial events. The process of laying out these vast ceremonial centers, with their pyramids, palaces, and ball courts arranged along sacred axes, would have required sophisticated surveying. It is highly plausible that they established a central null point, a conceptual ground zero, from which all other measurements and alignments radiated. This point might have been marked by a special stone, a temple, or the tomb of a founding ruler. From this origin, they could plot coordinates using their vigesimal system, using the concept of zero to define the starting line for their immense architectural projects. The city itself, in its precise layout, becomes a physical manifestation of a mathematical grid made possible by the invention of zero. The independent invention of zero in the Americas is more than just a historical footnote. It is a powerful corrective to outdated narratives about the development of human knowledge. It shatters the myth that profound abstract thought was the exclusive domain of the so-called Old World. The Maya developed a complex, functional zero without any contact with Indian or Babylonian scholars. They were driven by their own unique needs specifically, a deep cultural imperative to map time and align their world with the heavens. Their achievement stands as a monumental testament to the universality of the human mind's ability to generate brilliant, abstract ideas. When a Mayan scribe carefully painted a shell glyph into a codex, they weren't just leaving a blank space. They were giving form to nothingness, creating a mathematical concept that would, centuries later, become the bedrock of the digital age. It is a stunning reminder that genius can flower anywhere, and that some of humanity's most powerful ideas can emerge from the most unexpected places. Leaving behind the geometric ideals of Greece, our journey now takes us deep into the Cambodian jungle, to a temple complex that doesn't just use mathematics, but seems to breathe it in an entirely different way. Angkor Wat is not a structure you simply look at. It is an experience that unfolds around you, a vast and intricate labyrinth of stone that pulls you inward and upward through its repeating galleries and courtyards. As you walk its causeways, a fascinating pattern begins to emerge. The same architectural motifs, the distinctive lotus bud towers, the long, columned galleries, the concentric rectangular enclosures recur again and again, but they are not merely copied. They are scaled. The central tower cluster is the grandest iteration, but this same shape is echoed in slightly smaller towers at the gateways, and again in even more miniature forms adorning rooftops and spires. This is not simple repetition. It is a form of visual recursion where the core design pattern is nested within itself at different scales. To the modern eye, trained by computer graphics and natural sciences, this is unmistakable. We are witnessing the principles of fractal geometry, carved in sandstone centuries before the term was ever coined. This breathtaking architectural choice was almost certainly driven by something far deeper than a mere desire for decorative symmetry. Angkor Wat was built in the 12th century as a physical representation of Mount Meru, the sacred five-peaked mountain at the center of the universe in Hindu and Buddhist cosmology. This wasn't just a symbolic gesture, it was a deliberate attempt to create a functional model of the cosmos itself. In these belief systems, the universe is not a single, empty space. It is conceived as a series of nested realities, realms within realms, each containing its own mountains, oceans, and continents, all arranged in a vast, recursive hierarchy. The fractal design of Angkor Wat is the perfect architectural expression of this worldview. The largest enclosure wall represents the mountain ranges at the edge of the world. The next inner moat symbolizes the cosmic ocean. The central towers are the pinnacle of Mount Meru, and throughout, the repeating, self-similar structures at ever-decreasing scales create the palpable sensation that you are walking through one of these layered realities, that the entire complex is a microcosm containing the pattern of the macrocosm. The mathematics of the design was a direct conduit to the divine, a way to make the cosmological order tangible and navigable for the mortal worshipper. It is crucial to understand that the Khmer architects did not sit down with equations for the Mandelbrot set. They had no formal concept of fractal geometry as a mathematical discipline. What they possessed was a profound intuitive and cultural understanding of a pattern that is fundamental to both nature and human perception of beauty. They observed this pattern in the branching of trees, the structure of fern leaves, and the formation of coastlines. They understood that this kind of recursive scaling created forms that were both incredibly resilient and naturally beautiful. This intuition translated directly into their engineering. The repetitive, self-similar structure of the galleries and towers provided immense structural stability, distributing weight and stress efficiently across the vast complex, much like the branching pattern of a tree supports its canopy. The design is organic. It feels grown rather than built, which is perhaps why Angkor Wat, despite its immense size, seems to belong so completely to the jungle that embraces it. This blurring of the line between art and mathematics is what makes Angkor Wat such a powerful example of ancient genius. The builders were not applying a cold, calculated formula. They were weaving a cultural narrative, a spiritual map, and an artistic masterpiece using the innate language of pattern and form. Their achievement demonstrates that some of the most advanced mathematical ideas can be grasped and expressed through intuition, observation, and a deep desire to mirror the structure of the natural and cosmic world. Angkor Wat stands not as a puzzle to be solved with modern math, but as a testament to a different kind of knowing, one where art, faith, and mathematics were inseparable threads in the same magnificent tapestry. Stepping from the fractal jungles of Cambodia into the soaring stone forests of medieval Europe, we encounter a world where architecture was not just seen, but profoundly felt and even heard. The great Gothic cathedrals, like the magnificent Chartres, represent a breathtaking fusion of engineering audacity and spiritual aspiration. But to view them only as marvels of structural technique is to miss their deepest secret. These vast spaces were meticulously designed according to the same mathematical principles that govern musical harmony, creating a silent symphony in stone that was believed to resonate with the very music of the cosmos itself. The architects of these divine monuments operated on a profound belief inherited from ancient Greek thinkers like Pythagoras, that the universe was constructed from number and sound, a concept known as the harmony of the spheres. They held that the planets in their orbits produced ethereal, inaudible tones, and that the mathematical ratios found in pleasing musical chords were the same ratios that underpinned all of creation. A cathedral, therefore, was not merely a building, it was an instrument designed to tune the human soul to this celestial frequency. This philosophy was made tangible through the deliberate use of specific, powerful ratios. Walk the nave of Chartres Cathedral, and you are walking through a physical manifestation of a musical scale. The ratio of 1 to 2, which in music gives us the perfect octave, the most fundamental and consonant interval, might be expressed in the relationship between the height of the side aisles and the height of the central nave. The ratio of 2 to 3, which produces the rich, stable sound of a perfect fifth, could be found in the proportion of the width of the transept to the length of the choir. Even the ratio of 3 to 4, which creates a harmonious fourth, might be discovered in the dimensions of the crossing square. These weren't arbitrary aesthetic choices. They were a conscious application of Pythagorean harmonics, a way to build divine consonance into the very fabric of the church. The belief was that worshippers, surrounded by these perfect proportions, would be subtly elevated, their spirits harmonized and drawn closer to God through the invisible, mathematical order of the space. The cathedral became a massive resonator for the soul, but how did medieval masons, often illiterate, translate these abstract ratios into tons of stone and mortar? They relied not on complex arithmetic but on sacred geometry, a visual and practical language of compass and straightedge. One of their most powerful tools was the vesica piscis, or vessel of the fish. This shape is created by the overlapping of two circles of the same radius, with the center of each lying on the circumference of the other. Within this elegant, almond-shaped form, a treasure trove of harmonic ratios is naturally encoded. The width to the height of the vesica piscis inherently contains the square root of 3, a key irrational number, but more importantly for the builders, the geometric construction effortlessly produces the ratios for the octave, the fifth, and the fourth. A master builder like the famous Villard de Honnecourt, whose sketchbook reveals countless geometric diagrams, would use this single construction to generate the entire plan and elevation of a cathedral. He could swing his compass from point to point, deriving every critical dimension from the previous one, ensuring that the entire structure remained in a state of perfect proportional harmony from the largest arcade down to the smallest window tracery. This synthesis of math, music, and masonry represents one of the most holistic worldviews in human history. For the medieval mind, there was no separation between science, art, and religion. They were all different expressions of a single divine truth. The mason's careful setting out of a floor plan using the vesica piscis was as much an act of prayer as the priest's celebration of the Mass. Every measurement was a meditation, every ratio a revelation. The cathedral stood as the ultimate proof of this unity, a building that was at once a feat of engineering genius, a profound work of art, and a powerful spiritual engine. It challenges our modern, compartmentalized understanding of knowledge and reminds us that the greatest human achievements often emerge from the courageous desire to weave all of existence into a single, magnificent, and meaningful whole. Just as the Gothic architects of Europe were harmonizing their cathedrals with musical ratios, an entirely different mathematical pattern was taking shape across the Atlantic, woven into the very fabric of pre-Columbian thought. We now turn to a deceptively simple arrangement of numbers, a triangle where each number is the sum of the two directly above it. To the modern world, this is Pascal's triangle, named for the 17th century French mathematician Blaise Pascal, who studied its properties. But stunning archaeological evidence suggests that the intellectual ancestors of this pattern were being used, and perhaps even understood, by Mesoamerican cultures like the Olmec and Zapotec over 1,000 years prior. This isn't about finding a stone tablet neatly labeled with the triangle. It's about recognizing the same numerical fingerprint on ancient artifacts, revealing a mind grappling with combinatorial mathematics. The evidence emerges from intricate carvings and painted codices. On certain ceramic vessels and ritual objects, we find designs featuring stacked rows of dots or bars, arranged in a distinct triangular formation. The numbers in each row often correspond perfectly to the sequence of binomial coefficients: 1, then 1, 1, then 1, 2, 1, then 1, 3, 3, 1, and so on. For cultures without a formal written number system as we know it, these dot patterns were a visual, tactile way of representing numerical relationships. But why would they need this? The application was likely profoundly practical and spiritual. The Zapotec, for instance, developed one of Mesoamerica's earliest calendar systems. Calculating the complex interactions of different calendar cycles like the 260-day sacred round and the 365-day solar year requires understanding combinations and permutations. How many different ways can a specific day name combine with a number? This is a classic combinatorial problem, and the triangular arrangement of numbers provides a ready-made lookup table for these calculations, a Stone Age spreadsheet for time itself. Their use almost certainly extended into the realm of divination and cosmology. Priests and shamans were not just timekeepers, they were interpreters of fate, seeking to understand the myriad possibilities of events influenced by the gods. The different paths through the triangle could have represented the branching possibilities of future outcomes, a mathematical map of destiny. A specific combination of numbers might correspond to a particular omen or a recommended ritual action. In this sense, the triangle was more than a calculator. It was a symbolic representation of cosmic balance and the interconnectedness of all things. The number 1 at the apex could symbolize a unified source, which then divides and multiplies into the diverse complexity of the world, yet all remains connected by the underlying rule of summation, a beautiful metaphor for creation itself. This leads us to a tantalizing, though more speculative, question. Could this combinatorial logic have influenced the very layout of their cities and monuments? While we lack direct blueprints, the philosophical concept of balanced duality and layered reality was central to Mesoamerican thought. The design of ceremonial centers often reflected a belief in a layered cosmos, the underworld, the earthly realm, and the heavens. The recursive, expanding nature of the triangular pattern where each tier builds upon the last, is a powerful visual analog for this worldview. It is not difficult to imagine that the same intellectual framework that produced the number triangle also informed the symbolic planning of plazas, platforms, and temples, arranging them in tiers that represented this cosmic order. The city layout itself might become a physical expression of this mathematical growth, a giant mandala of expanding possibilities. The profound implication of this discovery is not that the Olmec or Zapotec knew it as Pascal's triangle, but that the human mind, when confronted with the problems of counting, chance, and cosmology, seems to naturally stumble upon this specific pattern. It is a pattern that emerges independently in the work of Persian mathematicians, Chinese scholars, and Indian poets. This recurrence suggests something fundamental about human cognition and our perception of order. The binomial coefficients aren't invented, they are discovered because they are a latent truth within mathematics itself, waiting to be uncovered by any culture that looks deeply enough into the nature of numbers and combinations. The pre-Columbian artifacts bearing this pattern are therefore not crude precursors to European math. They are independent testaments to the same universal truth, proof that the drive to find pattern and meaning is a shared human constant, whether expressed in the stone circles of Salisbury Plain, the harmonic arches of Chartres, or the dotted triangles of ancient Mesoamerica. As our exploration of ancient mathematical intuition continues, we arrive at the heart of the Roman Empire, where architecture was used not just for grandeur, but for storytelling on a monumental scale. Here, we find a fascinating example of a complex geometric form being used with breathtaking artistry, centuries before it would be formally understood by mathematicians. The Column of Trajan, erected in the year 113 to celebrate the emperor's victorious campaigns in Dacia, is far more than a simple victory monument. Its most striking feature is the magnificent helical frieze, a continuous ribbon of carved marble that winds its way from the base to the Capitol, telling a detailed narrative of the wars in over 150 scenes. But if you look beyond the carved soldiers and battles, you begin to perceive the underlying shape that makes this entire visual narrative possible, the elegant, ever-widening curve of a logarithmic spiral. This specific type of spiral is one of nature's most common and efficient growth patterns. Unlike the simple spiral of a coiled rope, which has a constant distance between its loops, a logarithmic spiral expands at a constant rate. This means each successive turn of the spiral is a consistent multiple wider than the last, creating a curve that grows outward while maintaining its same proportional shape. You can see this perfect form in the chambered Nautilus shell, where each new segment is a scaled-up version of the last, and in the immense arms of distant galaxies swirling through the cosmos. It is a shape that speaks of organic growth, of a natural and harmonious expansion. The frieze on Trajan's column follows this exact principle. The band itself widens almost imperceptibly as it ascends, ensuring that the sculpted scenes remain clearly visible from the ground below. This wasn't a random artistic choice. It was a brilliant optical solution achieved through a specific geometric intuition. The million-dollar question, of course, is whether the Roman architects and sculptors were consciously aware of the mathematical properties of the logarithmic spiral. The formal equation for this curve wouldn't be developed for another 500 years, with the work of mathematicians like René Descartes and Jacob Bernoulli. It's highly unlikely that a Roman engineer could have articulated the constant growth rate or the underlying exponential function. So how did they land on this precise form? The answer likely lies in a powerful combination of empirical observation and artistic genius. The Romans were masterful borrowers and innovators, and they were surrounded by examples of this spiral in the natural world. They observed it in the shells they collected, in the unfolding petals of a flower, and perhaps even in the curling horns of sacrificed animals. They understood intuitively that this particular curve was pleasing to the eye, that it created a sense of graceful, unforced movement. This intuitive grasp was then applied with breathtaking practical skill. The spiral frieze solves a major architectural and narrative problem: how to tell a long, linear story on a tall, cylindrical surface without the upper scenes becoming distorted and unreadable. By having the band widen as it climbs, the sculptors could maintain a consistent height for the carved figures throughout the entire narrative. A soldier carved near the base is the same size as a soldier near the top, because the space he occupies has grown to accommodate him. This creates a seamless visual experience for the viewer, whose eye is effortlessly guided upward by the gentle, natural curve. The spiral doesn't just tell the story of conquest. Its very form symbolizes the expanding power and eternal glory of Rome and its emperor. It represents an ascent, both physical and metaphorical, toward the heavens, where a statue of Trajan once stood. The choice of this specific curve transforms the column from a mere chronicle of events into a profound symbol of growth, power, and perpetuity. This subtle mastery is a testament to the Roman ability to blend the practical with the profoundly symbolic. They may not have had the calculus to define the spiral's rate of change, but they possessed an artist's eye for the patterns that nature herself uses to grow and build. The column of Trajan stands as a powerful example of how advanced mathematical concepts can be latent within a culture, expressed not through equations on a page, but through the intuitive language of form, proportion, and art. It reminds us that the human mind can grasp the principles of harmony and growth long before it can formally name them, and that some of our most enduring monuments are those that silently echo the deepest patterns of the universe itself. Venturing now into the sacred burial grounds of ancient China, we uncover a mathematical mystery that intertwines the pragmatic with the profoundly spiritual, revealing a civilization that saw numbers not just as tools but as guardians. The grand imperial tombs of the Tang dynasty, such as the magnificent Qianling Mausoleum, are not random assemblages of statues and structures. When viewed from above, their layout reveals a deliberate and puzzling order. The arrangement of spirit-way statues, the lines of stone officials, animals, and guardians that lead to the tomb mound often fall into distinct numerical groupings. And these aren't just any numbers, they are the prime numbers 3, 5, 7, and beyond. This pattern resonates deeply with a famous mathematical algorithm known as the sieve of Eratosthenes, a method for isolating prime numbers by systematically eliminating all their multiples. While the ancient Chinese certainly didn't call it by that Greek name, the conceptual parallel is striking. It suggests a ritualized process of selection, a way to sieve out the impure composite numbers to arrive at the sacred, indivisible primes for use in the most important architecture of all, the emperor's final resting place. To understand why these specific numbers were so revered, we must step into the Chinese cosmological worldview, where mathematics and metaphysics were inseparable. Prime numbers, by their very definition, are indivisible. They cannot be broken down into equal whole number parts. This inherent quality made them powerful symbols of unity, strength, and incorruptibility, perfect attributes for protecting the soul of a son of heaven on its perilous journey to the afterlife. In Chinese numerology, odd numbers were considered heavenly and auspicious, representing the active male yang energy, while even numbers were earthly and passive, representing yin. The primes, being almost exclusively odd, were the ultimate expression of celestial power. The number 3 symbolized heaven, earth, and man, the 3 realms of existence. 5 was the number of the cardinal directions and the elemental phases that composed the universe. 7 represented the stars of the Big Dipper, the celestial clock that guided fate. Using these numbers in the tomb's design wasn't mere decoration. It was a form of geomancy, a way to align the microcosm of the burial site with the macrocosm of the heavens, ensuring eternal harmony and divine protection. The practical application of this principle can be seen in the very stones of the Kynling mausoleum. The spirit way is punctuated by distinct groups of statues. You might find a cluster of 3 pairs of animals followed by a group of 5 civil officials, and then a set of 7 military officers. This isn't a haphazard placement. It is a numerological code, a series of protective wards written in stone. Each prime number grouping acted as a metaphysical barrier, a checkpoint against malevolent spirits who, according to ancient belief, could only travel in straight lines and were confused by patterns based on these indivisible numbers. The entire tomb complex becomes a kind of spiritual filtration system, sieving out chaotic and evil influences just as the mathematical sieve isolates primes, allowing only the pure and harmonious energies to reach the emperor's spirit. The architects were, in effect, using the immutable laws of mathematics to construct a fortress of eternity. We must, of course, acknowledge the speculative nature of this interpretation. Unlike a Babylonian tablet covered in clear calculations, the evidence here is architectural and symbolic. There is no surviving edict from a Tang emperor that explicitly states, "Use the sieve of Eratosthenes to plan my tomb." The proof is in the persistent, recurring pattern that aligns perfectly with what we know of Chinese spiritual and mathematical beliefs. This challenges us to expand our definition of what constitutes a mathematical artifact. It doesn't always have to be an equation on a page. Sometimes the most profound mathematical statements are made with the placement of a stone statue, the length of a pathway, or the grouping of pillars. The Tang tombs stand as a monumental synthesis of logic and belief, where the abstract purity of prime numbers was harnessed to achieve the most human of desires, to honor the dead, to seek protection from the unknown, and to create a lasting order that would withstand the ravages of time itself. Shifting our gaze from the ordered numerology of Chinese tombs to the sun-drenched courtyards of medieval Spain, we encounter a world where mathematics doesn't just protect or measure, it transcends into a state of pure spiritual ecstasy. Islamic architecture, exemplified by the breathtaking Alhambra Palace in Granada, represents one of history's most sublime marriages of abstract thought and tangible beauty. Here, every surface, every wall, ceiling, and archway is alive with an explosion of geometric patterns, interlocking stars, swirling arabesques, and infinitely repeating tessellations that seem to vibrate with a life of their own. To the casual observer, this is sheer decorative splendor, but to the mathematicians and architects who conceived it, this was the visual expression of a profound and advanced algebraic understanding, one that required solving complex cubic equations to bring these visions to life. This was not mere ornament, it was a theological statement, a philosophical argument, and a mathematical tour de force, all rendered in stone, tile, and stucco. The intellectual engine behind this visual revolution was the work of pioneering scholars like the Persian polymath Omar Khayyam. In the 11th century, while Europe was still in the early medieval period, Khayyam was writing his treatise on demonstration of problems of algebra, where he classified and solved cubic equations where the highest power is 3. These are far more complex than linear or quadratic equations, often representing the intersection of a parabola and a circle. Why would an architect care about such abstractions? The answer lies in the desire to create perfect, complex, and interlocking patterns. to design a flawless 12-pointed star that fits seamlessly within a hexagonal tile, or to subdivide a space into ever smaller, self-similar patterns, requires a precise understanding of angles, lengths, and areas. The solutions to these cubic equations provided the mathematical key to generating the proportions needed for these incredibly sophisticated geometric constructions. The master builders of the Alhambra may not have been solving equations on parchment at the construction site, but they were working from pattern books and using geometric tools, compasses, and straightedges whose underlying principles were dictated by this advanced algebra. Each intricate tile was a frozen snapshot of an algebraic solution. This drive toward infinite geometric complexity was deeply rooted in Islamic theology and philosophy. A central tenet of Islam is the prohibition of idolatry, which extended to a general avoidance of figurative art in religious contexts. This artistic constraint was not a limitation but a liberation. It forced artists and architects to explore a different, more abstract language of meaning. Instead of depicting the creator, they sought to evoke the creator's attributes, his infinite nature, his unity, and the underlying order of his creation. What better way to symbolize infinity than with a pattern that can repeat forever without a seam? What better way to express divine unity than with a design where every single piece, no matter how small, is integral to the beauty and stability of the whole? The recursive subdivisions and star polygons that cover the Alhambra's walls are a direct visual metaphor for this worldview. They represent a universe that is not chaotic, but meticulously ordered and bound together by unseen mathematical laws. Gazing upon these patterns is meant to be a meditative act, drawing the viewer from the contemplation of beautiful forms to an appreciation of the divine intellect that conceived such perfect order. The resulting effect is nothing short of visual poetry. Walking through the court of the lions or the hall of the Abencerrage is an overwhelming sensory experience. The patterns are so dense, so perfectly executed, that they create a sense of awe and hypnotic wonder. Your eye is led on an endless journey across the surface, tracing lines that flow from one shape to another, forever moving yet forever balanced. This is the genius of Islamic geometric design. It is dynamic yet perfectly static, infinitely complex yet perfectly orderly. It achieves the ultimate goal of sacred architecture, to use the material world to point toward the immaterial, to use the human mind's grasp of mathematics to hint at a divine mind whose understanding is infinitely greater. The Alhambra stands not as a palace of hedonistic pleasure, but as a university of the soul, its walls teaching lessons of unity, infinity, and harmony to all who are willing to look beyond the surface and perceive the profound mathematical beauty within. From the intricate tessellations of the Alhambra, we now journey to a realm where mathematics transcends geometry and algebra to grapple with the very nature of infinity itself. In the ancient spiritual traditions of Jainism, founded in India around the 6th century BCE, we find a cosmological vision so vast, so staggeringly immense, that it required a numerical language bordering on the transcendental to even begin its description. The Jain texts, meticulously preserved by monastic scholars, don't just speak of thousands or millions of years. They chart cosmic cycles lasting incomprehensible spans of time, numbers so large they defy human intuition. One of the most famous units is the palya, a period of time measured by the amount it would take to empty a gigantic cubic vessel, several miles wide, filled with fine sheep's wool, if one single strand were removed only once every century. The number of years this represents is astronomical, on the order of 10 to the 21st power, a number with 22 digits. To put that in perspective, it's a scale that dwarfs the age of our entire universe as understood by modern science. This wasn't meant to be a literal, calculable time frame, but a metaphorical device, a numerical symbol for the concept of the infinite itself. This profound engagement with the immense is physically manifested in the art and architecture of Jain temples. Elaborate mandalas and intricate carvings on temple walls often depict these cosmological numbers, not as dry statistics, but as part of the visual narrative of the soul's journey. You might see concentric circles representing layers of the universe, each annotated with these vast numerals, illustrating the countless lifetimes a soul must undergo to attain liberation from the cycle of rebirth. The numbers are woven into the iconography of the samsara chakra, the wheel of existence, emphasizing the nearly infinite scale of time and space through which consciousness must travel. The temple itself becomes a three-dimensional map of this cosmology, and the numbers are the coordinates on that map, guiding the devotee's meditation on a scale that is truly cosmic. This use of mathematics is fundamentally different from the practical engineering of the Romans or the harmonic ratios of the Gothics. Here, numbers are used not to build physical structures, but to construct conceptual frameworks for understanding existence. A fascinating and nuanced question arises: can we truly call these Jain numbers transcendental in the modern mathematical sense? Today, a transcendental number is formally defined as a real number that is not a root of any non-zero polynomial equation with integer coefficients. Famous examples include pi and Euler's number e. The Jain numbers are not irrational or transcendental numbers themselves. They are immense but finite integers. However, their philosophical application is what makes them a conceptual precursor. The Jains were using these finite numbers as a ladder to approach the idea of the qualitatively infinite, the ananta, or that which is without end. They were employing finite arithmetic as a tool to point toward a reality that lies beyond all calculation and measurement. In this sense, they were grappling with the same sublime, unknowable frontier that mathematicians would later formalize with the concept of transcendental numbers. Both are attempts to use the language of mathematics to describe that which is inherently beyond complete description, the infinite complexity of the cosmos and the nature of reality itself. This metaphorical and spiritual use of immense numerals reveals a different facet of humanity's relationship with mathematics. For the Jains, the ultimate goal was not calculation, but liberation, a release from the confines of the material world. These vast numbers served a deeply psychological purpose. By contemplating time spans of 10 to the 21st power years, the individual soul and its earthly concerns are rendered utterly insignificant. This isn't meant to induce despair, but rather a profound humility and a shift in perspective. The numbers are a spiritual technology designed to dismantle the ego, to shock the mind into recognizing its tiny place within an almost infinite universe, and thereby to catalyze a turning inward toward the eternal, unchanging soul or jiva. The mathematics becomes a form of meditation, a way to use the logical mind to ultimately transcend its own limitations and grasp at the sublime. The legacy of Jain cosmology is a powerful reminder that numbers are not just for measuring and building. They are also for wondering, for yearning, and for mapping the deepest mysteries of existence, proving that the quest to quantify the infinite is one of the most enduring and profound journeys of the human spirit. Imagine a vast empire stretching thousands of miles across treacherous mountain ranges, all administered without a single piece of paper, without a single written word. This was the reality of the Inca civilization, and their solution to this immense logistical challenge was as elegant as it was enigmatic: the quipu. At first glance, a quipu is a simple, almost primitive artifact, a main cord from which hang dozens of secondary cords, tied with a bewildering array of knots. For centuries, scholars viewed them as mere mnemonic devices, simple memory aids for storytellers. But a radical and thrilling theory is now emerging, suggesting these knotted strings were something far more sophisticated. They may represent one of the world's earliest and most unique applications of a binary logic system, a precursor to the Boolean algebra that powers every single digital device on the planet today. The genius of the quipu lies in its multi-layered language of variables. The primary layer was undoubtedly numerical. The Incas used a base 10 positional system, where a knot's value was determined by its position on the string. A figure 8 knot represented the number 1. A long knot could represent 2 through 9 depending on the number of turns, and a single overhand knot signified a multiple of 10, 100, or 1,000 based on its placement. This alone was a powerful accounting tool used to track vast inventories of grain, livestock, and population across the empire, but the information didn't stop there. The physical characteristics of the chords themselves added another dimension of meaning. The color of a chord derived from specific dyes could denote the subject matter, a yellow chord for gold, a brown one for potatoes. The material cotton or wool might indicate the region the data came from. The spin direction of the plied thread, whether Z twist or S twist, could even convey a positive or negative value, a concept of yes or no, true or false. This is where the connection to Boolean logic becomes so compelling. In the 19th century, mathematician George Boole developed a system of algebra where variables are not numbers, but logical states, true or false, represented by 1 and 0. This binary language is the absolute foundation of modern computing. The quipu, in its own way, seems to have been using a similar binary-like system for complex, non-numerical information. A specific color chord with a knot in a particular position might not mean 20 llamas, but rather a binary statement. The bridge on the Royal Road is Passa Ble, or the storehouses in the northern province are Full. The combination of these true/false, yes/no statements across multiple chords could create a rich, dense tapestry of logistical data, an entire report on the state of the empire encoded in cotton and knots. A messenger, or chasqui, could run for hundreds of miles carrying this lightweight, durable data storage device, delivering vital information to administrators who knew how to read this intricate code. The necessity of such a precise and reliable communication system becomes stunningly clear when you look at the crowning achievement of Inca engineering, Machu Picchu. Perched on a near-inaccessible mountain ridge, the construction of this city was a logistical nightmare. How did they coordinate the quarrying, shaping, and transportation of thousands of massive stone blocks? How did they ensure a constant supply of water and food for the workers? The answer almost certainly lies in the quipu. Administrators at the site could have used them to send requests for specific tools or more workers. Officials in the valley could reply with chords indicating the status of supplies, a green chord with a certain knot meaning shipment of bronze tools is delayed, or a red chord signaling additional laborers are en route. The perfect fitting of the stones, which required incredibly precise planning and measurement, could have been facilitated by quipus carrying architectural specifications, using knot positions and chord lengths to denote dimensions and angles. The entire city, in a sense, can be seen as a physical manifestation of the data once stored on now lost bundles of string. The true profundity of the quipu is that it completely shatters our conventional definition of writing and computation. We are so conditioned to equate information with written text that we fail to see that the Incas had developed a powerful, three-dimensional, tactile data storage system. It was a system every bit as complex as early cuneiform or hieroglyphics, but one that operated on a completely different principle. It challenges the very Eurocentric idea that civilization requires a phonetic script. The quipus stands as a monumental testament to human ingenuity, proving that the drive to record, compute, and communicate is a universal human constant, and that the language of logic can be woven not just in ink on a page, but in knots on a string, a tangible and enduring code that managed one of the greatest empires the world has ever seen. Now, let's dive into one of the most astonishing and humbling artifacts ever recovered from the ancient world, a discovery that single-handedly rewrites our understanding of Greek technological prowess. In the year 1901, sponge divers exploring a shipwreck off the coast of the Greek island of Antikythera stumbled upon a corroded, lumpy mass of bronze and wood. For decades, it sat in a museum drawer, largely ignored, its secrets hidden beneath centuries of calcified sea crust. It wasn't until the latter half of the 20th century, with the advent of X-ray and later CT scanning technology, that researchers finally peered inside. What they revealed was nothing short of mind-boggling. This wasn't a statue or a simple navigational tool. It was an incredibly complex clockwork machine, a precise analog computer now known as the Antikythera mechanism. Dating back to the 2nd or 1st century BC, this device contained over 30 precisely cut bronze gears, all meticulously engineered to model the motions of the sun, the moon, and the known planets against the backdrop of the stars. It could predict solar and lunar eclipses with remarkable accuracy, track the 4-year cycle of the ancient Olympic Games, and even account for the moon's subtle wobble in its orbit, a phenomenon known as lunar anomaly. But the most breathtaking feature of all, the one that truly connects it to our story, is its use of a specific, ingenious gear train that embodies a core principle of calculus centuries before the subject was formally invented. This revolutionary component is a pin and slot mechanism within the device's moon gear. To understand its brilliance, we need to grasp the problem it was solving. The moon doesn't orbit the Earth at a constant speed. Due to the elliptical shape of its orbit, it moves faster when it's closer to us and slower when it's farther away. If you were to model its motion with a simple, single gear rotating at a constant rate, your model would gradually fall out of sync with the real moon in the sky. The Greek engineers who built the Antikythera mechanism were perfectionists. They wanted a model that mirrored the heavens with impeccable accuracy. Their solution was a work of pure mechanical genius. They took 2 gears, one gear connected to the main drivetrain, rotated at a constant speed, representing the moon's average motion. This gear had a pin on its face that stuck out. That pin slotted into a gap on a second, subsidiary gear, which was itself connected to the hand that displayed the moon's position on the device's face. As the first gear turned at its constant rate, the pin engaged the slot on the second gear, but here's the magic. The slot wasn't at the center. The second gear was mounted off-center on its own axis. This meant that as the first gear turned, the pin would push and pull the second gear, alternately speeding it up and slowing it down in a smooth, rhythmic pattern that perfectly mimicked the moon's actual variable speed in its elliptical orbit. This mechanical arrangement is a direct physical analog of a fundamental concept in calculus, the calculation of a variable rate of change. In modern terms, the mechanism was solving a differential equation. It was taking a constant input rotation and transforming it into a non-uniform output rotation that accurately modeled a real-world, non-linear celestial phenomenon. This isn't calculus in the abstract, symbolic language that Newton and Leibniz would develop in the 17th century. There are no written limits, derivatives, or integrals on a parchment scroll explaining this device. This is calculus made tangible. This is calculus rendered in bronze. It represents a profound, practical understanding of modeling continuous change and motion, an understanding that was applied to solve a complex astronomical problem with breathtaking elegance. The Greeks may not have had the formal theory, but they unquestionably had the practical application. They were engineering with concepts that wouldn't be formally defined for another millennium and a half. The existence of such a sophisticated device naturally raises a profound and haunting question. What was the context for this invention? This mechanism wasn't a one-off fluke produced by a lone, unheard-of genius. The level of miniaturization, precision, and theoretical understanding it displays suggests it came from a vibrant tradition of mechanical engineering, a school of thought that has been almost entirely lost to history. The writings of Cicero and other ancient authors hint at this lost world, mentioning devices like the globe of the sky built by Archimedes. The Antikythera mechanism is the only physical evidence we have that these stories were true. It was likely built in a workshop in Rhodes, a known center of astronomical and mechanical learning, and may have been used by priests or scholars not just for curiosity, but for very practical religious and civic purposes. Knowing the exact timing of an eclipse was power. It could be used to awe the populace, to demonstrate a connection to the gods, or to plan important ceremonies. It could also have been a magnificent teaching tool, a portable planetarium for demonstrating the principles of the cosmos to students. Its discovery forces us to completely re-evaluate the narrative of scientific progress. We often picture history as a linear march forward, with a Greek miracle followed by a fall into the Dark Ages, and then a slow climb back up through the Renaissance and the Scientific Revolution. The Antikythera mechanism shatters that simplistic story. It shows us that a brilliant, alternative path of technological development existed in the ancient world, one based on precision gearwork and analog computation. This path was apparently lost, perhaps a casualty of the destruction of the great libraries like Alexandria, or the shifting priorities of a collapsing empire. The knowledge embedded in this device had to be painfully rediscovered over 1,000 years later. It stands as a powerful reminder that innovation is not inevitable. It can bloom in unexpected times and places, only to be forgotten, its seeds lying dormant for centuries before they find the right conditions to sprout again. The Antikythera mechanism is more than an ancient computer. It is a ghost from a future that never was, a stunning testament to a level of genius we are only now beginning to fully appreciate. While the ancient Greeks were crafting bronze gears to model the heavens and the Inca were tying knots to manage an empire, a different kind of mathematical genius was rising from the very soil of North America. Far from the academic centers of the Old World, Native American cultures were shaping the land itself into monumental earthworks that challenge our most fundamental assumptions about geometry. Take the Great Serpent Mound in Ohio, for instance. From the ground, its sinuous, quarter-mile-long form is a breathtaking work of art. But from above, it reveals something even more profound, a shape that simply cannot be contained by the rules of classical Euclidean geometry. This isn't a structure built from straight lines and perfect circles, the idealized forms that Euclid laid out in his Elements. The serpent's coils curve and undulate in ways that defy simple description with a compass and straightedge. They suggest an intuitive, almost innate understanding of curved space and complex topological principles concepts that wouldn't be formally defined by mathematicians for another 800 years. This empirical mastery of form was deeply intertwined with a celestial purpose. These mounds were not built in isolation. They were carefully positioned to engage in a silent, stone and earth dialogue with the cosmos. The Great Serpent Mound is a perfect example. Its head is aligned to point toward the setting sun on the summer solstice, while its coils may align with other astronomical events like the solstice sunrise or even the extreme rising and setting points of the moon. But the alignment isn't a simple straight line. The pathway the celestial body takes across the sky is an arc, a curve. By designing an earthwork that itself follows a graceful, meandering curve, the builders were creating a terrestrial mirror of that celestial motion. They were building a map of the sky on the ground, using a geometry that was organic, observational, and deeply connected to the rhythms of the natural world. This was mathematics born from watching the heavens, not from reading a textbook, a geometry of experience rather than abstraction. It is crucial to understand what these builders were not doing. They were not developing formal axioms or writing proofs. There is no evidence they had a theoretical concept of non-Euclidean geometry, the radical 19th century idea that space itself could be curved, giving us the elliptical geometry of a sphere or the hyperbolic geometry of a saddle shape. What they possessed was a brilliant practical and observational genius. Through generations of careful watching, they internalized the patterns of the sky. They understood that the relationship between the horizon and the moving sun was not a series of right angles but of sweeping curves. Their architecture reflects this deep empirical knowledge. The elliptical enclosures found at sites like Hopewell Culture National Historical Park are not perfect circles stretched out. They are precise ovals, requiring a sophisticated understanding of how to maintain a constant sum of distances from two fixed points. This is a geometric construction that implies a practical, rather than theoretical, grasp of conic sections. This distinction is what makes these earthworks so mathematically significant. They represent a parallel path to mathematical understanding, one that is deeply cultural and environmental. For these Native American cultures, the Earth was not a passive canvas but a sacred, living entity. Their most profound architecture was made from it, literally shaping their mathematical ideas from the soil beneath their feet. This earth-based mathematics stands in stark contrast to the paper-based mathematics that developed in Europe. It was a mathematics of place, of direct engagement with the environment, and of spiritual relationship with the cosmos. The serpent's curve isn't just a shape. It is a narrative, a symbol of rivers, of lightning, of spiritual journeys, all expressed through a form that resonates with the curved nature of the world they observed. The legacy of these mounds forces us to expand our definition of what counts as mathematical thought. We often privilege the written, formalized tradition that leads from Euclid to Newton. But the builders of the Serpent Mound demonstrate that profound mathematical intuition can be expressed through landscape, through art, and through a deep, generational conversation with the natural world. Their work prefigures modern geometry not because they had its theorems, but because they understood its truth on a visceral, experiential level. They built a vision of a universe that is not rigid and rectilinear, but fluid, dynamic, and wonderfully curved, a vision that modern science has only recently confirmed. These silent mounds of Earth are a powerful reminder that mathematics is a universal human language, but it has many dialects, each shaped by the unique culture and environment that gives it voice. While the Native American mound builders were mapping celestial curves onto the very Earth on the other side of the world, an even more abstract form of mathematical organization was being pressed into damp clay. In the fertile plains between the Tigris and Euphrates rivers, the ancient Mesopotamians faced a problem that was both profoundly practical and a constant source of social conflict: the annual flooding of their rivers. While these floods brought life-giving silt for agriculture, they also ruthlessly wiped away the boundary markers between fields. Every year, surveyors had to return to re-establish these boundaries and resolve disputes over who owned what land. It was from this mundane, bureaucratic necessity that one of humanity's most powerful mathematical tools may have emerged. Archaeologists have unearthed clay tablets, like the one known as Plimpton 322, that reveal something astonishing. These aren't simple lists of numbers, they are carefully organized arrays, grids of numbers arranged in rows and columns, used to systematically solve problems involving multiple unknowns. In essence, these are the earliest known examples of matrix algebra, a method for handling linear equations that wouldn't be formalized in the West for another 3,000 years. Imagine a complex inheritance dispute. A man dies, leaving behind several sons and a portfolio of assets, parcels of land of different sizes, numbers of sheep, and amounts of grain. Dividing this estate fairly according to the prevailing laws, which often stipulated specific fractions for each son, was a computational nightmare. The Mesopotamian scribe's solution was brilliantly methodical. He wouldn't try to solve it all in his head. Instead, he would take his stylus and draw a grid on a soft clay tablet. In one column, he might list the different types of assets. In the rows, he would record the stipulated fractions for each son. Then, he would perform a series of operations adding rows, scaling columns, searching for common multiples, all within this tabular format. He was manipulating the entire system of numbers as a single entity, not just crunching them one by one. This organized tabular approach is the fundamental spirit of matrix algebra. The scribe was seeing the relationships between numbers, not just the numbers themselves. He was working with a proto-matrix. The application of this systematic thinking almost certainly extended far beyond farmland and into the realm of monumental architecture. The construction of a ziggurat, a massive, tiered temple tower reaching for the heavens, was the ultimate civic project. It required the coordinated effort of thousands of workers and the management of vast quantities of materials. Millions of mud bricks, precisely cut stones, enormous quantities of bitumen for mortar, and wooden beams for reinforcement. How did the architects plan for the precise slope of each ascending tier? How did they calculate the amount of material needed for each level so that the structure remained perfectly balanced and stable? It is highly plausible that they used these same tabular methods. They could create a table where each row represented a level of the ziggurat, and the columns recorded the length, width, height, and thus the volume of material required for that level. By adding these columns, they could calculate the total demand for bricks and mortar. This wasn't just accounting, it was applied linear algebra. The structural integrity of the entire massive edifice, its ability to stand for millennia, may have relied on the computational power of these ancient arrays. What makes this discovery so revolutionary is what it reveals about the origins of abstract thought. We often picture mathematical breakthroughs as emerging from the minds of lone geniuses pondering pure theory in isolation. The Mesopotamian tablets tell a very different story. They show us that some of our most powerful abstract tools were born from the dirt under the fingernails needed to solve everyday problems. Matrix algebra didn't start as an esoteric branch of mathematics. It started as a tool for preventing fistfights between farmers and for ensuring that a temple wouldn't collapse under its own weight. This hidden computational layer exposes the deeply practical roots of abstraction. The Mesopotamian scribe, hunched over his clay tablet, wasn't trying to invent a new field of mathematics. He was just trying to be fair, efficient, and accurate. In doing so, he and his colleagues were laying the groundwork for a system that would, millennia later, become the absolute bedrock of our digital world, powering everything from computer graphics to economic models. Their legacy is a powerful reminder that the most profound intellectual revolutions often begin not with a grand theory, but with a simple, practical solution to a common problem. Now let's pivot from the abstract computations of Mesopotamia and return to the sun-scorched banks of the Nile, where we find a different kind of mathematical elegance at play, one that seems to draw its inspiration directly from the natural world. As you walk through the great hypostyle hall at the Temple of Karnak or the majestic colonnades of Luxor, you are surrounded by a forest of stone. The columns are immense, towering pillars carved to resemble papyrus stalks and lotus plants, creating the sensation of walking through an eternal, petrified garden. But if you were to take a step back and study the layout of these columns with a surveyor's eye, you might notice something subtle yet extraordinary about their arrangement. They aren't always laid out in a simple, uniform grid. In certain areas, the angle between the lines of columns, or the spacing from a central point, appears to approximate 137.5 degrees. This is no ordinary angle. This is the golden angle, a precise mathematical division of a circle that is intrinsically linked to the golden ratio. To understand the golden angle, picture a perfect circle. Now divide that circle into two parts so that the ratio of the smaller arc to the larger arc is the same as the ratio of the larger arc to the whole circle. This proportion is once again the golden ratio, approximately 1.618. The angle you get for the smaller arc is about 137.5 degrees. This specific angle is nature's favorite recipe for optimal packing and growth. It's the reason why the seeds in a sunflower head are arranged in such an efficient spiral pattern. It's the angle that dictates the placement of leaves around a stem, a phenomenon known as phyllotaxis, ensuring that each leaf gets maximum exposure to sunlight without shading the ones below it. It is a pattern of breathtaking efficiency and beauty repeated across the biological world, so why would we find it echoed in the stone columns of an Egyptian temple? The implication is staggering that the architects were not just building a structure, they were replicating a fundamental pattern of creation itself. The potential applications within the temple are as brilliant as they are poetic. These were not just buildings, they were stages for powerful religious dramas that unfolded with the rising and setting of the sun. The play of light and shadow was a critical part of the ceremonial experience. Imagine a high priest standing before a statue of a god at a precise moment at dawn. The strategic placement of columns at the golden angle could have been used to choreograph this light. As the sun ascended, its rays would filter through the colonnades, creating moving patterns of light and darkness that would highlight specific altars, statues, or hieroglyphs at specific times. The 137.5-degree angle is exceptionally good at creating these complex, non-repeating shadow patterns, ensuring that the illumination ceremony was unique and dynamic, a daily reenactment of the sun god Ra bringing order from chaos. This would blend solar alignment with deep aesthetics, using a mathematically perfect angle to enhance the spiritual power of the ritual. Of course, we must approach this idea with the same scholarly caution we apply to the golden ratio in the Parthenon. The evidence is often subtle and open to interpretation. The temples have been modified, damaged, and rebuilt over millennia, making it difficult to be absolutely certain of the original builder's intentions. It is entirely possible that this alignment is a beautiful coincidence, an emergent property of a design that simply felt right to the architects. They may have arrived at this angle through an intuitive process of trial and error, seeking a layout that felt harmonious and organic, much like the growth of a plant, without ever calculating the number 137.5. Their primary inspiration was, after all, the natural world, the very same world that is governed by this angle. In trying to recreate a papyrus marsh in stone, they may have unconsciously replicated its underlying mathematical blueprint. Yet, even if the use was unintentional, its presence is profoundly significant. It suggests a deep cultural affinity for the patterns that permeate the living world. The Egyptians were master observers of nature. Their entire cosmology was built upon it: the cyclical flooding of the Nile, the journey of the sun. The patterns of plants and animals were all seen as manifestations of the divine order, or mat. By incorporating these organic patterns into their most sacred architecture, they were striving to build a microcosm of that perfect divine order. The temple was meant to be a slice of the perfectly ordered cosmos here on Earth. Therefore, a colonnade that subconsciously mirrors the growth pattern of a plant is, in fact, more sacred and more perfect than one built with simple right angles. It is more in tune with the universe. This blurring of the line between the intentional and the intuitive is what makes Egyptian architecture so endlessly fascinating. It challenges our modern desire to always find a calculated, written-down reason for everything. It allows for the possibility that a culture can be so deeply steeped in an observational, naturalistic world that its greatest works of art automatically resonate with the mathematics of life, creating a sacred harmony that feels both innate and eternal. Imagine the scene over 3,000 years ago on the plains of ancient India, where the air hums not with machinery, but with the intensity of a different kind of precision. A group of Vedic priests, their minds steeped in complex ritual, are not just chanting hymns, they are executing one of history's most extraordinary fusions of faith and mathematics. Their sacred text, the Sulba Sutras, which literally translates to the codes of the cord, lays out the rules for constructing elaborate fire altars, or yajna vedis. But these are no ordinary piles of brick. The scriptures dictate that these altars must be built in specific, intricate shapes: falcons with outspread wings, tortoises, chariot wheels, and complex isosceles triangles. The stakes for getting it right could not be higher. It was believed that the slightest error in the altar's dimensions would not just ruin the ceremony, it could disrupt the very cosmic order the ritual was designed to maintain. The success of a harvest, the birth of an heir, the victory in a battle, all were thought to hinge on the geometric perfection of a sacred shape built in the earth. This immense pressure for perfection is what drove these ancient scholar priests to become groundbreaking mathematicians, developing techniques that eerily prefigure one of algebra's most powerful tools, the binomial theorem. The central challenge they faced was one of area conservation, but with a profound ritual constraint. The texts often required transforming one shape into another of identical area. For instance, a priest might be instructed to construct a square altar, but then later, for a different ritual, he must transform that same square into a rectangle or even a circle, all without adding or losing a single speck of Earth's area. This is a deceptively complex puzzle. How do you calculate the side length of a square that has the exact same area as a given rectangle? The Sulba Sutras provide the answer with a stunningly elegant formula. They instruct the priest to take the length of the rectangle, divide it into two unequal parts, and then use those parts in a specific calculation involving squares and square roots. What they are describing in a purely geometric form is the essence of the binomial theorem, the algebraic rule for expanding expressions that are raised to a power, like a plus b2. They didn't have our modern algebraic notation with letters and exponents, so they expressed it all through geometry, using the chord and stakes of a surveyor to physically manipulate areas and side lengths. When they stated that the diagonal of a rectangle produces both areas which its length and breadth produce separately, they were articulating the geometric version of the Pythagorean theorem, a special case of the broader mathematical reasoning they were mastering. This was far more than theoretical gymnastics. It was a matter of intense practical and spiritual necessity. The construction process was a ritual in itself. The priest would use a cord, the ultimate symbol of measurement and order, to lay out the altar's precise proportions. The entire ceremony was a symbolic reenactment of creation, with the altar representing the universe in miniature. Its geometric perfection was believed to generate a specific spiritual energy or to attract the favor of a particular deity. A falcon-shaped altar, for instance, was used in rites aimed at attaining heaven, its form symbolizing ascent. The mathematical precision ensured the form was true and therefore effective. This turns the entire construction process into a breathtaking act of bridge building. The priest, through mathematics, was building a bridge between the physical world of mud brick and measured cord and the invisible spiritual world of cosmic forces. The correctly solved equation was the key that unlocked the door between realms, making the altar a true conduit for divine interaction. The mathematician was, in that moment, also the highest form of priest. The profundity of this achievement places ancient India in a unique position in the global history of mathematics. While the Babylonians had their tables of Pythagorean triples and the Egyptians their empirical formulas, the Vedic scholars were operating at a more abstract level. They were manipulating general rules and formulas that could be applied to a whole class of geometric problems. They weren't just calculating a specific altar size. They were developing a generalized procedure for area transformation. This move from the specific to the general is the very heart of algebraic thinking. It demonstrates a conceptual leap that is often attributed to much later mathematicians. The Sulba Sutras show us that the seeds of this abstract reasoning were being planted not in a university, but at a smoky fireside, driven by a culture's deepest desire to connect with the cosmos through the universal and eternal language of number and form. Their legacy is a powerful testament to the idea that some of our most profound intellectual inquiries are born not from cold curiosity, but from a fiery, spiritual need to find order and meaning in the universe. Now we journey to the oldest living culture on Earth, to a landscape where mathematics is not written in stone or on tablets, but painted on rock walls and sung in stories passed down for over 60,000 years. Here, in the ancient rock art of Aboriginal Australia, we find what may be the most organic and intuitive expression of mathematical thinking in human history. To the untrained eye, these paintings might appear as abstract patterns of dots, concentric circles, and meandering lines. But to the Aboriginal people, these are far more than decoration. They are intricate maps, complex legal documents, and sacred narratives. And remarkably, many of these designs exhibit a breathtaking visual complexity that seems to prefigure one of the most modern fields of mathematics, chaos theory. These patterns aren't just random, they possess a fractal-like quality where similar motifs repeat at different scales, and they often embody the core chaos theory principle of sensitivity to initial conditions, where a tiny change in one part of the system can lead to vastly different outcomes elsewhere. This is mathematics emerging not from academic study, but from a deep, generational conversation with a dynamic and unpredictable environment. Consider the classic dot painting style from the Central Desert. From a distance, these works look like a field of stars or a topographic map seen from the sky. Up close, you see that they are composed of countless individual dots, often arranged in swirling patterns that curve and flow around each other. These patterns are not symmetrical in a rigid Greek sense. They are organically complex, much like the branching of a river delta, the pattern of cracks in dry earth, or the unpredictable spread of a bushfire. This is the visual language of a people who live in a land of extreme and often chaotic natural forces. They observed that a single lightning strike in one location could lead to a fire that would reshape the landscape for hundreds of miles, that a small change in wind direction could mean the difference between finding water and perishing. Their art captures this reality. The placement of each dot is deliberate, yet the overall pattern feels emergent and dynamic, perfectly mirroring the behavior of the natural systems they depended on for survival. It is a visual representation of a world where small causes have enormous and often unforeseeable effects. This artistic expression was deeply functional. These patterns were central to songlines, or dreaming tracks, intricate oral maps that wove navigation, law, and mythology into a single narrative. A painting might represent a specific waterhole, but the dots and lines radiating from it would tell the story of the ancestral beings who created it and chart the path to the next safe camp. The fractal nature of the design was crucial. A large circle might represent a major mountain, while a smaller, identical circle next to it might represent a specific rock formation near its base. This recursive scaling allowed a single artistic convention to convey information across vast geographical scales, from a continental overview down to the location of a single berry bush. The art was a mnemonic device for storing an enormous density of information about a landscape that was both physically and spiritually alive. The sensitivity of the pattern, the idea that moving one dot could change the entire story, was a powerful metaphor for the interconnectedness of all things and the profound responsibility that comes with every action. The profound implication is that this represents a form of mathematics that is fundamentally different from the Western tradition. It wasn't about calculation, proof, or abstraction for its own sake. It was an embodied mathematics, a mathematics of observation and pattern recognition that was directly applied to the urgent tasks of living. It was a mathematics that emerged from the body itself, from the rhythm of walking the land, from the act of painting with a hand, from the cadence of a song that describes a journey. This challenges the very definition of what mathematics is. We often confine it to numbers and equations, but the Aboriginal example shows us that mathematics can also be a way of seeing, a way of organizing knowledge about a complex and interwoven world through visual and narrative patterns. Their rock art is a testament to a different kind of genius, one that understood the chaotic and fractal nature of reality long before mathematicians gave it a name, and one that chose to encode that understanding not in textbooks, but in stories, songs, and the silent, enduring language of art on stone. Imagine a world without clocks, where the only way to know the hour was by reading the subtle, shifting language of shadows cast by the sun. For the ancient Greeks, this wasn't a limitation. It was an invitation to apply their greatest intellectual passion, geometry, to the very fabric of daily life. While we've marveled at their grand temples and philosophical theorems, some of their most ingenious mathematical creations were designed for a far more humble purpose, telling time. Among these was a very special and somewhat mysterious curve known as the quadratrix. Its story begins not with a sundial, but with one of geometry's most frustrating problems, trisecting an angle. Using only a compass and a straightedge, the tools of the Greek geometer, dividing an angle into two equal parts was simple, but dividing it into three equal parts. That was one of the famous three classical problems of antiquity, and it was proving to be impossible with those basic tools. Then, in the 5th century BC, a brilliant and rather boastful mathematician named Hippias of Elis made a spectacular breakthrough. He decided to break the rules. He invented a new curve generated by a combination of two motions that could solve the problem effortlessly. This was the quadratrix. Here's how it worked conceptually. Picture a square. Now, imagine a horizontal line sweeping down from the top of the square to the bottom at a constant, steady rate. At the very same time, a radius line is sweeping from the left side of the square to the right side, also at a constant rate. Now, track the point where these two moving lines intersect over time. The elegant, sinking curve traced by this intersecting point is the quadratrix. Its true power was revealed when you extended it. This curve could not only trisect any given angle, but could actually divide an angle into any number of equal parts. For the Greeks, this was a theoretical thunderclap. It was a mechanical solution to an abstract geometric problem, a tool of incredible power. But what does a curve that divides angles have to do with telling time? The connection is one of beautiful, logical symmetry. A sundial is, at its heart, a device that translates the circular journey of the sun across the sky into a linear measurement of time on a dial face. The shadow cast by the central gnomon moves in a circular arc, but the hour lines we need to read must be marked out in evenly spaced increments. This creates a fundamental problem. How do you accurately divide the arc of the sun's path into equal units of time? This is essentially a problem of dividing angles. During the equinoxes, the sun's path is a perfect arc, and dividing that arc into 12 equal parts for the 12 hours of daylight is precisely the kind of challenge the quadratrix was born to solve. While no physical sundial has been unearthed with an explicit engraving of the quadratrix curve, the mathematical knowledge was undoubtedly in the air. Scholars like Ptolemy and later mathematicians wrote about using the properties of such curves for constructing precise astronomical instruments. It is highly plausible that the master craftsmen who engraved the complex, often non-uniform hour lines on sophisticated Greek sundials, used the geometric principles underlying the quadratrix to ensure their markings were perfectly accurate. They may have used a mechanical linkage or a careful geometric construction inspired by Hippias's idea to lay out these lines with precision, transforming a theoretical marvel into a practical tool for priests, philosophers, and citizens to organize their day. This elusive connection between the quadratrix and the sundial is profoundly significant because it represents a hidden current in the history of science. We often celebrate the grand monuments and the formal written theorems, but the true engine of progress is often found in these quiet, practical applications of abstract thought. The quadratrix likely wasn't carved on a temple pediment for all to admire. Its value was in its utility. It was a concept that lived in the minds of scholars and the skilled hands of artisans, a bridge between the pure world of geometric theory and the human need to measure, to schedule, and to comprehend the rhythms of the cosmos. The sundial was more than a timepiece. It was a symbol of order, a way to impose human reason on the celestial dance. By employing a curve like the quadratrix, even indirectly, the Greeks were demonstrating their deepest belief that the universe is mathematically structured, and that by understanding its geometry, we can not only solve abstract puzzles but also navigate the very flow of time itself. This hidden application reminds us that the boundaries between pure and applied mathematics are often far more porous than they appear, and that some of history's most brilliant ideas are those that quietly shape our daily lives from the shadows. High in the Andes, the Inca faced an engineering nightmare that would keep any modern architect awake: how to build an empire in the world's most active seismic zone, using massive, irregular stones and without any mortar to hold them together. Their solution was so brilliant and so counterintuitive that it defies belief. At sites like Sacsayhuaman, they constructed colossal walls from a chaotic-looking jigsaw puzzle of granite blocks, each one uniquely shaped, yet all fitting together with a precision that denies a sheet of paper entry into the seams. This wasn't just artistry, it was a high-stakes mathematical strategy. The prevailing theory is that the Inca master stonemasons intuitively harnessed the principles of modular arithmetic, a branch of number theory that deals with remainders and cycles. to create these immortal, earthquake-proof structures. Imagine a world without standard units of measurement like inches or meters. How would you ensure that thousands of differently shaped blocks, quarried from different locations by different teams, would all fit together perfectly on site? The Inca likely used a system based on congruence. They may have established a set of preferred modular dimensions for the length, width, and height of their blocks. A block size wouldn't be a random number. It would be designed so that its key dimensions were all congruent modulo a certain number. In simpler terms, this means that when you divide a block's length by this base number, the remainder would be the same as when you divide its height by that same number. This creates a hidden consistency, a rhythmic pattern within the apparent chaos. A mason at the quarry could rough out a block to these modular specifications. Then, at the construction site, instead of trying to match one unique, irregular shape to another, the builders were essentially working with a system of standardized remainders. They knew that any two blocks shaped to the same modular rule would, by the laws of mathematics, be compatible. The final, painstaking process of dressing the stones to achieve that legendary snug fit was about fine-tuning within a pre-established mathematical framework, not about creating infinite uniqueness. This system provided its most critical benefit when the ground began to shake. A rigid, mortared wall is brittle. When a seismic wave hits it, it has no flexibility and simply cracks apart. The Inca's modular, mortarless walls were designed to dance. During an earthquake, the individual blocks in a process called kinetic energy dissipation. They jiggle, they slide minutely, they even bounce slightly, but the modular design and the intricate interlocking shapes ensure they always find their way back to equilibrium when the shaking stops. The energy of the quake is dissipated through friction between the stones and their complex movement, rather than being concentrated into a single, catastrophic fracture point. The wall literally moves as a living entity and then settles back into place, often in better condition than the modern concrete buildings around it. The true genius of this system is that it was almost certainly not documented in any written codex we've discovered. The knowledge was likely embedded in the culture itself, passed down through apprenticeships, encoded in the physical tools and templates used by the masons, and refined through centuries of empirical observation and practical experience. They felt the mathematics in their hands and saw it in the stability of their structures, long before a European mathematician like Gauss would formalize the theory of congruence in the 19th century. The Inca didn't need the abstract notation. They had the proof in the timeless, unmortared walls of Sacsayhuaman, which have withstood 500 years of earthquakes that have toppled countless later constructions. Their legacy is a powerful lesson in intuitive engineering, demonstrating that a deep understanding of mathematical principles can be embodied in culture and craft, creating monuments of breathtaking resilience that continue to whisper their secrets to those who know how to listen. Stepping from the earthquake-resistant stonework of the Incas into the serene courtyards of a Moorish palace is like walking from a lesson in rugged engineering into a masterclass in ethereal, abstract beauty. In places like the Alcazar of Seville, your gaze is inevitably drawn downward, not to the ground beneath your feet, but to a breathtaking universe unfolding across the floor. This is no ordinary tile work. It is a mesmerizing sea of interlocking stars, polygons, and spirals that stretch to infinity without a single gap or overlap. This is the art of tessellation perfected to a level of mathematical sophistication that would not be formally understood in the West for centuries. Every single tile, every line, every color is part of an immense and precise puzzle, a frozen symphony of geometry that whispers secrets of infinity, unity, and a culture that saw no divide between scientific rigor and spiritual devotion. The sheer intellectual achievement embedded in these floors is staggering. To create a pattern that can repeat across an infinite plane without any breaks or errors is a profound mathematical challenge. It requires solving complex tiling problems that belong to a field of modern mathematics known as group theory, which classifies the ways symmetrical patterns can be constructed. The Moorish artisans had to intuitively grasp concepts like periodic functions, the idea that a pattern repeats at regular intervals, and symmetry groups, which are the complete sets of ways a pattern can be rotated, reflected, or shifted and still look the same. Their designs are built from a handful of fundamental tiles, often star-shaped polygons, which are then combined and repeated using a set of precise geometric rules. They employed intricate compass and straight-edge constructions to generate these shapes, then devised the transformational rules to make them fit together perfectly. This was not a process of random artistic trial and error. It was a rigorous mathematical algorithm executed in ceramic and mortar. The palace floor was, in effect, a massive physical proof of advanced geometrical theorems. This drive for such breathtaking complexity was born from a powerful theological imperative. A central tenet of Islamic art is the avoidance of figurative imagery in sacred contexts, a principle known as aniconism. This was not a limitation but a divine invitation to explore a different, more abstract language for representing the universe. If one cannot depict the Creator through images of his creation, how does one evoke his attributes? The Moorish solution was to use mathematics. The infinite, seamless repetition of their tessellations became a direct visual metaphor for the infinite and indivisible nature of God, or Allah. There is no beginning and no end to the pattern. Every point is the center, and every tile is essential to the whole. This symbolizes the divine unity, or Tawhid, the concept that all creation is interconnected and emanates from a single, unified source. Gazing upon these floors was meant to be a meditative, almost hypnotic experience, drawing the worshipper from the contemplation of beautiful, orderly forms to an appreciation of the supreme intellect that conceived such perfect, eternal order. The palace was not just a home for a ruler, it was a gateway to the sublime, and the mathematics in its floors was the key. The most stunning implication of this artistic revolution is that it fundamentally flipped the traditional relationship between art and science. We often think of art as applying pre-existing scientific discoveries using the laws of perspective, for instance. But in the case of Moorish tessellations, the opposite occurred. The intense artistic and spiritual desire to create these infinitely complex patterns is what drove mathematical innovation. The artisans were essentially exploring the boundaries of geometrical possibility, pushing up against the limits of what could be constructed with their tools. In their quest for ever more beautiful and complex patterns to glorify God, they were inadvertently, or perhaps quite deliberately, pioneering new mathematical territories. They were asking and answering questions about symmetry, recursion, and periodicity that would not be formally posed in European mathematics for hundreds of years. Their work stands as a powerful testament to the idea that human creativity, especially when fueled by deep spiritual yearning, can be one of the most potent engines of scientific discovery. The Alcazar's floors are more than just beautiful decorations. They are a silent stone library of mathematical intuition, a testament to a culture that understood that the path to the divine was paved with the eternal and perfect language of geometry. Now, let's journey into the heart of a scorching desert, where ancient architects devised a form of air conditioning so elegant it required no electricity, only a deep, intuitive understanding of the wind itself. In the historic cities of Persia, like Yazd, The skyline is punctuated by magnificent, towering structures that look like giant chimneys rising from the flat rooftops. These are badgers or wind catchers, and they are masterpieces of passive cooling that have been providing relief from the blistering heat for over 1,000 years. At first glance, they appear to be simple ventilation shafts, but a closer look reveals a breathtakingly sophisticated application of physics, specifically the principles of fluid dynamics that would much later be formalized by the Swiss mathematician Daniel Bernoulli in the 18th century. The Persian builders may never have written down an equation, but their structures solve them perfectly in brick and clay. The magic of the badger lies in its ingenious design, which expertly manipulates air pressure and flow. Bernoulli's principle, in its modern formulation, states that as the speed of a fluid or air increases, its pressure decreases. The wind catcher harnesses this phenomenon with remarkable precision. The tower is strategically oriented to face the prevailing wind, and its top is open but often features cleverly angled panels or a central divider. As the wind blows against the tower, it is forced to accelerate over these obstructions and through the narrowed vents. According to Bernoulli, this increase in wind speed causes a drop in air pressure at the top of the tower. Meanwhile, on the opposite leeward side of the structure, the air remains relatively still and at a higher pressure. This pressure differential is the engine of the entire system. The low pressure at the top essentially acts as a vacuum, actively sucking the hot, stale air up and out of the living quarters below. But the process doesn't stop there. As this air is exhausted, it creates a suction that draws cool air into the home from a very specific source, often an underground water channel called a kanat or a central courtyard pool. This incoming air is cooled evaporatively as it passes over the water's surface before circulating through the rooms, creating a continuous, refreshing breeze without a single moving part. What is truly staggering is that this entire complex thermodynamic process was engineered through painstaking observation and generations of trial and error, not mathematical calculation. The master builders were brilliant empiricists. They knew from centuries of lived experience in the desert that a tall tower caught more wind, that a narrow opening accelerated it, and that a curved inlet could direct it more efficiently. They observed how air moved through their buildings and made incremental adjustments to the badger's height, its cross-sectional shape, the number and angle of its openings, and its integration with other architectural elements like basements and water sources. This was science learned by doing, refined over centuries and passed down as a craft from one generation of builders to the next. They didn't need to know the formula for pressure drop. They could see its effects in the way a curtain fluttered or feel it in the coolness of a room on a blazing afternoon. Their buildings became the physical embodiment of a principle they understood in their bones long before it was named. This story of the wind catcher offers a profound counterpoint to the traditional narrative of scientific discovery. We often envision progress as a linear path from theoretical insight to practical application. First comes the equation, then comes the invention. The badger turns this model completely on its head. Here, the practical application came first by millennia. The engineering marvel existed for ages, performing its magic silently in the desert, waiting for science to eventually develop the language to explain why it worked so perfectly. The Persian architects achieved through intuitive design and meticulous craftsmanship what later scientists would achieve through calculus and experimentation. This reminds us that the human drive to solve problems and create comfort is a powerful engine of innovation in its own right, one that can often arrive at sophisticated solutions through a different, more tactile path of knowledge. The badger is not a crude precursor to modern air conditioning. In many ways, it is its superior, a sustainable, energy-free, and breathtakingly elegant solution to a fundamental human need: proving that some of the most advanced engineering in history was accomplished not with calculators, but with wisdom carved by the wind itself. Now, let's turn our attention from the abstract beauty of Moorish palaces to the hard, practical reality of empire building on an unprecedented scale. The Romans are famous for their legions, their aqueducts, and their law, but perhaps their most enduring and mathematically fascinating achievement is the vast network of roads that stitched their empire together from the misty highlands of Scotland to the sun-baked sands of Egypt. These were not mere dirt tracks worn down by countless feet. They were monumental engineering projects built with deep foundations, cambered surfaces, and meticulous drainage to last for centuries. And if you were to look at a map of this immense network, connecting major cities, military forts, and key ports, you would see something that looks remarkably like a giant graph theory problem solved in stone and gravel. This is the hidden mathematics of Roman logistics, a brilliant, intuitive application of principles that wouldn't be formally defined for another 2,000 years. At the heart of graph theory are three simple concepts: nodes, edges, and paths. A node is a point of connection, like a city. An edge is a link between two nodes, like a road. And the core problem is finding the most efficient path between two nodes, minimizing either distance, time, or cost. The Roman road network is a breathtaking physical manifestation of this abstract idea. The nodes were their newly founded coloniae, their strategic army camps, and their bustling trading hubs. The edges were the famous via, the straight, unswerving roads that connected them. And the relentless drive was always to find the shortest, most efficient path between these critical points. Roman surveyors, known as agrimensors, were the masters of this craft. They would set out with their simple but effective tools, the groma for sighting straight lines and the chorobates for leveling, and their primary directive was efficiency. They aimed to conquer distance, to reduce the time it took for a legion to march to a restive frontier or for a shipment of grain to reach the hungry capital. In doing so, they were instinctively solving what we now call the shortest path problem, the very cornerstone of network optimization. This wasn't an academic exercise, it was the absolute lifeblood of the empire. The military necessity is the most obvious. A rebellion could flare up in a distant province, and the ability to rush the nearest legion to the scene along a direct, all-weather road could mean the difference between a quick suppression and a full-scale war. The roads were the empire's nervous system, and the swift movement of soldiers was its immune response. But the economic implications were just as profound. Efficient roads lowered the cost of trade dramatically. A merchant could move goods from Hispania to Rome with fewer days on the road, meaning less expense for animal feed, fewer paid nights in inns, and a lower risk of spoilage or banditry. This economic integration is what made the Roman Empire more than just a collection of conquered territories. It created a unified economic zone where goods, ideas, and people could circulate with unprecedented freedom. The road network literally built a common market spanning 3 continents. The true genius of the system, however, lies in its emergent hierarchy, a concept deeply familiar to modern network theorists. The Romans didn't build all roads equally. They created a clear hierarchy, vast, stone-paved via publici for long-distance, high-speed travel, smaller via vicinales connecting regional towns and villages, and simple via privati leading to individual estates. This is a perfect analog to the hierarchical networks we design today for data or transportation, where major backbone connections handle the heaviest traffic and smaller feeder lines distribute it locally. This structure prevented congestion and ensured that traffic flowed logically from the local to the global and back again. Furthermore, the famous milestone, or milarium, found alongside every major road was more than just a signpost, it was a data node. It gave a traveler precise information about their location within the network, allowing for better route planning and resource management. Cumulatively, these milestones provided the Roman administration with a complete digital map of their empire's connectivity, etched in stone rather than silicon. We must be careful, of course, not to project a modern mathematical framework onto an ancient civilization. There is no evidence that a Roman engineer ever articulated the concept of a graph or a node. They would have explained their actions in purely practical terms, the need for speed, for security, for control. But that is precisely what makes their achievement so compelling. It demonstrates that powerful mathematical principles can be discovered and applied through sheer pragmatic necessity, long before they are formally understood and named. The Roman road network stands as a colossal, thousand-year experiment in applied graph theory, a testament to the fact that the human mind can grasp the logic of networks and efficiency through the demands of real-world problems. The stones of the Appian Way are silent, but they speak volumes about a civilization that understood, in its bones, that the shortest path between 2 points is not just a geometric truth, but the key to building and maintaining a world-spanning empire. High in the Himalayas, Tibetan monks engage in one of the most ephemeral and profound artistic rituals on Earth. They spend days, sometimes weeks, meticulously pouring millions of grains of colored sand onto a flat surface, constructing an intricate, awe-inspiring geometric diagram known as a mandala. Upon its completion, after it has been used for its sacred purpose, they perform a ceremony of breathtaking impermanence. They sweep it away, releasing the sand into a flowing river. This act reminds us that the true power of the mandala was never in its physical permanence, but in its function as a spiritual tool, a cosmic map, and a meditation aid. And at the heart of this map lies a secret language of symmetry so precise, so mathematically sophisticated, that it can only be fully described using concepts from linear algebra that wouldn't be formalized for centuries. The mandala is a perfect physical expression of invariance under transformation, a concept at the very core of eigenvectors and eigenvalues. To grasp this connection, we need to demystify these mathematical terms. Imagine a linear transformation as a specific kind of change applied to a space, like stretching, compressing, rotating, or reflecting it. An eigenvector is a very special arrow within that space, a direction that remains stubbornly unchanged in its essential nature by the transformation. The transformation doesn't destroy it or point it somewhere new. It might only stretch it or shrink it. The amount by which it stretches or shrinks is its eigenvalue. Think of it as a kind of mathematical integrity. The eigenvector stays true to its direction, even when the entire world around it is being warped and altered. Now look at a classic Tibetan mandala. It is almost always radially symmetrical, built from a central point, or bindu, from which the entire universe of the design emanates in perfect, balanced layers. The primary action, the fundamental transformation you can perform on a mandala, is rotation. If you rotate the entire intricate design by a specific angle, say 90 degrees or 45 degrees, depending on its structure, the whole pattern maps perfectly onto itself. It looks exactly the same as it did before you rotated it. The directions along which this symmetry holds, the axes that remain unchanged and define the rotation, are the mandala's eigenvectors. The number of times the pattern repeats in a full rotation relates to its eigenvalues. The monks, through sacred geometric texts and oral tradition, had discovered the recipes for creating these perfectly invariant forms without any of our modern notation. This was not an exercise in abstract art for its own sake. Every single element of the mandala, from its outermost square gates to its innermost circle, is a densely packed symbol representing different aspects of the universe and the mind. The perfect symmetry is a mirror of the cosmic order, a depiction of a balanced and harmonious universe, but its purpose is turned inward. The monk in meditation doesn't just look at the mandala. They are instructed to mentally dismantle it, to deconstruct its intricate layers and then reconstruct them, visualizing it with their mind's eye in 3 dimensions. This intense mental act of visualization and transformation is a form of cognitive training. By holding the invariant structure of the mandala in their mind while mentally rotating and navigating through it, they are, in a very real sense, performing a spiritual version of a linear transformation. They are learning to find the eigenvectors of their own consciousness, the core, unchanging nature of awareness that persists even as thoughts, emotions, and sensations, the constant transformations of mind, arise and pass away. The mathematical perfection of the external sand painting becomes a tool to discover the internal, eternal witness. This reveals a stunningly different pathway to mathematical discovery. In the West, our trajectory often moved from practical application to abstract theory. We developed calculus to solve physics problems, then generalized it. The Tibetan approach was the inverse. They started with a metaphysical, spiritual goal to understand the nature of reality and the mind. In their quest to create a perfect symbolic representation of this reality, they intuitively landed upon the same deep mathematical principles. Their genius was not in calculating eigenvalues but in embedding them into a ritual art form. The rules for constructing a mandala, passed down through generations in texts like the Vajravali, are incredibly precise geometric recipes. They dictate every proportion, every division of the circle, every relationship between the concentric layers. This ensured that any monk following the rules would produce a structure possessing this perfect rotational symmetry. They encoded the mathematics into the ritual itself, into the very act of creation. The mandala, therefore, is more than art and more than a prayer. It is a frozen theorem, a spiritual device that uses the universal language of symmetry to guide the practitioner toward a direct experience of the invariant, unchanging reality that underlies all of the universe's beautiful and ultimately impermanent transformations. Standing back from these 30 incredible examples, a breathtaking panorama begins to emerge from the dust of ages. From the golden ratio in Greece to the fractal patterns in Cambodia, from the prime numbers in Egypt to the binary logic of the Inca, we see a tapestry of human ingenuity woven across millennia and continents. It's a picture that forces us to ask a monumental question. How is it that cultures separated by impassable oceans and vast stretches of time all arrived at the same profound mathematical truths? The answer seems to lie in a beautiful duality, a combination of 2 powerful forces shaping human history. On one hand, we see the undeniable spark of independent discovery, the universal human mind grappling with the same fundamental problems of survival, cosmology, and meaning. The human brain, no matter where or when it develops, is wired to recognize patterns. We see symmetry in nature. We observe the cyclical motion of the heavens, and we instinctively seek order in the chaos of existence. This shared cognitive toolkit, this innate ability to perceive rhythm, proportion, and number, is our common inheritance. It's why the elegant growth pattern of the Fibonacci sequence could intuitively find its way into both a Hindu temple and a European cathedral, even if the builders used different names and different reasons for its power. It's why the concept of a right angle and the triangle that defines it became a global tool for construction, from the Babylonian surveyors to the megalithic architects of Europe. This is mathematics as a native language of the human species, emerging spontaneously wherever complex society takes root. Yet, there is also the tantalizing possibility of whispered connections, of knowledge traveling along ancient trade routes we can barely imagine. The Silk Road was not just a path for silk and spices, it was a highway for ideas. Could the concept of zero have traveled from India to the Maya? It's a controversial and fiercely debated idea, but the simultaneous development of such a revolutionary abstract concept in two isolated parts of the world is a stunning coincidence. Perhaps the Greek knowledge of the Antikythera mechanism's gearing was not entirely lost, but seeped eastward, influencing the development of complex machinery in other cultures. We may never find the archaeological smoking gun that proves these direct links, but the recurrence of such specific and complex ideas, like the precise value of pi or the principles of harmonic ratios, suggests that our ancestors were far more interconnected than our history books often portray. They were not primitive peoples isolated in their own little worlds. They were intrepid explorers, traders, and thinkers, sharing and refining ideas across vast distances. This doesn't diminish their genius, it amplifies it, showing a world where knowledge was the most precious commodity, passed from hand to hand and generation to generation, each culture adding its own layer of understanding and application. This grand synthesis invites us to make a fundamental shift in how we view these stone marvels. We must stop seeing them merely as tombs, temples, or palaces. We must start seeing them as libraries, but these are not libraries filled with parchment and ink. They are libraries of stone, of space, of proportion, and of alignment. The Great Pyramid is not just a pharaoh's burial chamber. It is a three-dimensional textbook on geometry and geodetics. Angkor Wat is not just a temple to Vishnu. It is a lecture hall on fractal cosmology. The Parthenon is not just a house for a statue of Athena. It is a timeless seminar on aesthetic philosophy and the mathematics of beauty. The knowledge within them is not written in a language that can be easily translated, but in a language of number, form, and celestial relationship that requires us to measure, to calculate, and to think in entirely new ways. They are the hard drives of the ancient world, storing the most vital data of their cultures in a format designed to last for millennia, waiting for a future civilization with the right tools to finally come along and boot them up. We are that civilization. Our technology, our lasers, our satellites, our particle detectors are giving us the first real chance to read these libraries in their entirety. Every new scan, every new precise measurement is like turning a page in a book we are only just learning to read. Ultimately, this journey through mathematical mysteries reveals something far more profound than the intelligence of our ancestors. It reveals their deepest hopes and their most driving fears. They were not just building for the present, they were building for eternity. They were trying to create something permanent in a world of impermanence, to etch their understanding of the cosmos into the very bedrock of the planet. They sought to align their lives, their deaths, and their societies with what they perceived as the eternal, unchanging laws of the universe, laws written in the language of mathematics. In doing so, they left behind a legacy that is both a gift and a challenge. The gift is this incredible repository of knowledge, a testament to the universal power of the human mind. The challenge is to approach it with a new humility, to shed our modern arrogance and recognize that the timeline of discovery is not a straight line from primitive past to enlightened present. It is a complex branching tree with many limbs lost to time and many fruits we are only now rediscovering. These 30 concepts are not 30 closed cases. They are 30 open doors inviting us to step through and continue the conversation they started thousands of years ago. A conversation about who we are, our place in the cosmos, and the beautiful, mysterious language of numbers that binds it all together. And so our incredible journey comes to a close, a voyage that has taken us across continents and through millennia, From the sun-baked deserts of Egypt to the misty highlands of Scotland, from the intricate temples of India to the colossal earthworks of North America. We've stood in the shadows of 30 magnificent monuments, each one whispering a different secret in the universal language of mathematics. What began as an exploration of stone and geometry has unfolded into something far greater, a profound recognition of the human spirit's relentless drive to measure, to understand, and to connect with the cosmos itself. These structures are so much more than tombs or temples. They are the permanent record of our ancestors' most brilliant thoughts, a collective library of human ingenuity written not in ink, but in alignment, proportion, and stone. The most humbling realization is how this global tapestry of knowledge forces us to completely rewrite the story we tell ourselves about progress. For so long, the history of mathematics was presented as a straight, linear path, a relay race of genius from the Greeks to the Enlightenment and into the modern era. What these monuments reveal is that this story is not just incomplete, it is fundamentally wrong. Innovation is not a linear march. It is a complex branching tree with roots sinking deep into every culture on Earth. The Babylonians were using Pythagorean triples 1,000 years before Pythagoras. The Maya developed the concept of zero without any contact with the rest of the world. Greek engineers were building analog computers capable of modeling the heavens' irregular motions. This wasn't a slow, primitive crawl toward understanding. It was a brilliant, multifaceted explosion of insight happening simultaneously across the globe. These ancient builders challenge our modern arrogance, reminding us that genius is not a product of our technology, but of our boundless curiosity. This changes everything about how we should look at these sites. The next time you see a picture of the Great Pyramid or stand before the Parthenon, I urge you to see it not as a static relic of a dead civilization, but as an open question. See it as a challenge left for us by the past. Each precise ratio, each celestial alignment, each encoded constant is a message in a bottle, waiting for us to finally decipher its full meaning. With every new technological advance with ground-penetrating radar, laser scanning, and particle physics, we are gaining new tools to read these messages. We are not just archaeologists and historians, we are detectives, piecing together a puzzle that spans the entire human experience. The greatest lesson these stone sentinels teach us is that the drive to uncover the universe's secrets is what truly defines us. Our ancestors looked up at the same stars we see today and felt the same awe, the same burning need to find their place in the grand scheme of things. They used the best tools they had: chisels, cords, and their own brilliant minds to engrave their understanding into the planet itself. They built bridges between the earth and the sky, between practical need and spiritual yearning, and they built them to last forever. That legacy is now ours to protect, to study, and to build upon. So I encourage you to step outside, look up at the night sky, and feel that same connection. Let it ignite your own curiosity. Share your thoughts, your theories, and your wonder in the comments below. Let's continue this conversation together. And if you've enjoyed this deep dive into history's greatest enigmas, make sure to subscribe and hit that notification bell so you don't miss our next adventure into the unknown. Thank you for watching, and never, ever stop